Bom dia a todos os presentes, né? Vamos dar, então, início ao segundo dia do simpósio sobre a colaboração científica na área de física entre a França e o Recife, evento este que faz parte das comemorações dos 50 anos do Departamento de Física da UFPE. Now I'll change to English. Good morning and good afternoon to you all. I'm José Tabosa, and I would like to welcome all the speakers and all the participants in this second day of our symposium on the France-Recife Collaboration in Physics. So, as I announced yesterday, today we are pleased to have the presence of Monsieur Sébastien Dayol, attaché de coopération et d'action culturelle of the French Consulate in Recife. He will also welcome the participants and present his view on this scientific collaboration. But before that, I just want, on behalf of the Physics Department, I really would like to, again, to warmly acknowledge and thank the French Consulate in Recife for their financial support for the realization of this symposium. Now, I'm pleased and happy to invite Monsieur Sébastien Dayol to welcome the participants. So, please.
Bom dia, estou aqui. Obrigado. Vou falar em português, não sei se está ok. Me informaram que era uma apresentação em português. Pode ser?
Okay, pode ser, sim.
Bonjour à tout le monde également. Bom, primeiro, obrigado pelo convite, né? Como você falou, sou Sébastien Dayol, adjunto de cooperação e ação cultural no Nordeste, da Embaixada da França. E então, a Embaixada apoia a cada ano mais ou menos 20 eventos científicos franco-brasileiros no Nordeste. E esse ano, realmente, um prazer para a gente apoiar essa celebração dos 50 anos do Departamento de Física da UFPE, porque essa celebração realmente testemunha dessa longa história que a França tem com essa grande instituição de pesquisa na área da física no Brasil desde já os anos 70. Queria só aproveitar essa pequena introdução para lembrar que essa relação entre nossos dois países ela foi construída ao longo dessas relações humanas, né? Das visitas de pesquisadores, como, por exemplo, ouvi falar da vinda dos professores Claude Cohen-Tannoudji, Serge Roche, ambos recebedores de um prêmio Nobel de Física, e como hoje, com a presença do professor, diretor Albert Fett. E essa colaboração também, já faz muitos anos que ela está se fortalecendo, também com esses programas essenciais, né? Os programas de cooperação bilaterais, muito importantes, criados entre os dois governos, do Brasil e da França, e em particular com os projetos CAPES e FECUB. E então, ainda para a gente, acho que para todo mundo, é mais importante lembrar, ainda mais nesse período de crise internacional que a gente está passando, que a ciência, o conhecimento e realmente essas trocas de ideias entre países e culturas, elas têm esse potencial de trazer soluções. E essas soluções são soluções em comuns para os desafios que todo mundo vai ter para o futuro e que a gente precisa fortalecer essas relações nesse objetivo. Então, não vou falar muito mais, queria desejar ainda muitos anos de cooperação entre os pesquisadores brasileiros e franceses. E, de novo, então, meus parabéns para o Departamento de Física da UFPE e parabéns para toda essa organização desse evento lindo. Obrigado, José.
Ok, obrigado também pela sua participação, né? E mais uma vez agradeço agora em português, né, o suporte, né, e o apoio que recebemos do consulado francês aqui em Recife. Obrigado. Okay. So now let's move on. Okay, so now we have the presentation of the first talk of the session, which will be presented by Professor Albert Fert, and we are really pleased to open this section. And Professor Albert Fert is Nobel laureate in physics 2007, and I just want to say that we are really honored to have his participation in this symposium. And to introduce Professor Fert, I invite our emeritus professor and former Minister of Science and Technology of Brazil, Professor Sérgio Rezende. So please, Sérgio, have the screen.
Thank you, Tabosa. I'm sorry to all of you because I had trouble in getting into the room. Good morning, everyone. It's my pleasure and a great honor to introduce Professor Albert Fert. First, I'd like to thank you, Fert, for being with us today, celebrating the 50 years of our physics department. Professor Fert has had a long time collaboration with Brazilians, but not specifically with us. Myself and my colleague, Antonio Azevedo, met him many times in conferences and workshops, exchanged ideas by email, but we were not fortunate, like other colleagues, that interacted directly with him. But he was in Recife once. In the year 2000, he came to the International Conference on Magnetism that we organize here. Albert Fert graduated the École Normale Supérieure in Paris, and he obtained a doctoral degree in a joint program between Grenoble and Paris. And he became a professor at the University of Paris in Orsay in the 70s, and he's been working there for 50 years. Now he's an emeritus professor at Orsay. In 1988, Fert in Orsay and Greenberg in Munich independently discovered the giant magnetoresistance effect in magnetic multilayers. Actually, the first author of the paper of Fert reported in GMR is Mario Babish, our colleague from Rio Grande do Sul, who was working with Fert as a postdoc. This discovery made possible the development of very sensitive read-ahead devices that revolutionized the magnetic recording industry. And they are used now in all magnetic hard disk drives. The discovery also gave birth to the field of spintronics, which is the most important area of magnetism in the last times. In 2007, Albert Fert and Peter Greenberg received the Physics Nobel Prize for their remarkable discovery. They were good friends. Unfortunately, Greenberg passed away a few years ago, and Fert wrote a very nice article in Nature about their friendships about Greenberg. Fert is still very active all the time in physics, publishing very great papers, and you see what he has been doing during the last years in his talk from topology to devices, example in spintronics. Thank you, Albert, very much for your presence here today.
Thank you. Can you hear me? Okay, the sound is okay?
Perfectly.
Okay, so thank you very much, Sergio. I am very pleased to see you in person since 5 years when you were in Greece with me in the workshops. So good morning, everybody. It's good morning for you. And I am very pleased to be today with many Brazilian friends, also French friends, and maybe friends, other friends in the world in the community of physics. So my attraction for Brazil, my love for Brazil, goes back a very long time ago. At the beginning, physics was not in the game. Yeah, yeah. At the beginning, when, for example, teenager and after, I was mainly attracted by the Brazilian culture, literature, and music. And I remember teenager when I was very attracted by the novel of Jorge Amado. Dona Flores, Seus Dois Maridos, Gabriela, Teresa Batista. Certainly at this time, I was a teenager in love of some of these young mulatas, the Jorge Amado, Gabriela, maybe, or another one. And then student in Paris. The discovery was the discovery of the cinema novo. That is Carlos Dieguez, Glauber Roche. And I was looking at this film, attending in the small cines of Quartier Latin or in the Cinémathèque in Rue du Hulme, close to École Normale Supérieure, where I was. Okay, so I know very well this time of the cinema and maybe also film of today. And then later, when I was about 30, my wife and I had good friends in Rio de Janeiro. And so we spent at this time, around 20 for me, we spent vacations, holidays in Rio, Cabo Frio, Búzios, Salvador de Bahia, of course. And it was a time of the fantastic discovery of the music of the La Bossa Nova. So I remember, maybe if young people know the names, Chico Buarque de Holanda, Edu Lobo, Vinicius de Moraes, of course, and Maria Batista, Maria Bethânia, Elis Regina, Maria Creusa. So I remember long nights during these holidays in nightclubs of Copacabana to listening to this music, or in small places downtown. I don't remember the name of this place. Gafiora is the name. Small place for samba, for dancing.
Lapa,
and so,
Lapa and Cinelândia.
Yeah. Okay. And today I am still a fan of Brazilian music. And so my strong relation with the Brazilian physics started a little after, when I had students or postdoc, or postdoc from Brazil. And the first one was from Porto Alegre, was Paulo Purer. And so he did a fantastic job on the property of spin glass, certainly that need to be revisited today. Okay, sometime I am revisiting some work of a long time ago. And then Mario Babiš has been cited by Sergio. And Mario Babiš, of course, participated to our first research on multilayers and participate to the discovery of the GMR, and is the first author of the most cited paper on the GMR. Then Dante Mosca of Curitiba has also a very excellent paper that we had together with also people in Michigan State University on GMR. And after them, there were other people from Porto Alegre, Fernando Shep, with Gustavo Pereira. And of course, and I say that not only Dante Mosca from Brito, but today in our lab, we have a student of Dante, which is Nicola Figaredo. And so the other relation, as has been told by Sergio, we a good friend and somebody that I esteem a lot and admire is Sergio Rezende. And we have often some exchange about idea or some suggestion. So, and I was very happy when a few years ago, he accepted to participate to a symposium that I was organizing in Greece, in the island of Spetses. And the school was, okay, I can change. Okay, I can share the screen now. So the screen, where is my, sharing the screen. I want to share. OK, partager. OK, I don't know how it is now. OK, Zoom. There is something built with, no. So I try to, I have something on my screen.
Professor?
Yeah.
When
Okay,
you press...
maybe I can. So I am here, I am on my PowerPoint. I'm going back to the Zoom. And then, yeah.
You
It
press
says that.
share screen. Your
Yeah,
PowerPoint.
okay, I press, but I don't see my PowerPoint on the screen. Okay, I see it. Okay. Okay, so you can see it. Huh? Okay, so I was.
Yeah, we see it now. Okay.
Okay, so I was very happy to invite Sergio to this school on spin-orbit coupling and topology, on the interplay between topology and physics. And in fact, so you see the talk given by Sergio. He was also in this field of topology and physics. And this is a photo of the village of Spezes. The school was just around the corner. And I remember that Sergio did not go to the school by coach, not by taxi boat, but he was going with this motorcycle. Do you remember? This photo is in a street of Spezze. Do you remember this motorcycle, Sergio?
Perfectly well, yes.
Yeah.
Very well.
And then my talk today will be to a continuation of these workshops and to continuation to this physics of interplay between topology and physics, but it will be a little farther. It's from topology to physics and device, because we are 5 years after, and now topology is going towards device. Okay, so I begin my scientific talk. And so I begin with the first, a simple example of topologic particle, topologic structure is the skyrmions. It's simpler to explain. If you have a magnetic layer with upward, the magnetization upward, this is the classical picture of a skyrmions, a local configuration of the atomic spins going from up, like in the layer, on this edge, rotating in this time counterclockwise to become down at the center and continuing this rotation in the same direction, that is counterclockwise, to become up on the other edge, as in the magnetic layer. And so this is a configuration that is described as topologically protected. And the concept has been introduced by Skyrm a long time ago in particle physics. And that means in this particle case, after this, you see when there is always the same counterclockwise rotation or clockwise, you cannot distort progressively continuously this structure to come back to the initial trivial structure of the ferromagnetic layer. And so there is this structure. This protection is important for the property of this particle and is characterized by this topological number associated to these rotations. And so this, in fact, in most cases, this topological structure are induced by Diouloshinsky-Moria interaction of this type. So this interaction that makes that rotating from S1 to S2 clockwise of counterclockwise gives opposite energy. And so this explains, this is the stabilization of this structure. And this Diouloshinsky-Moria interaction has been first introduced by Olszewski-Moria for non-centrosymmetric oxides with super exchange. Then with Peter Levy, we extend the concept to metallic structure. This, of course, to have this Olszewski-Moria interaction, you need large spin-orbit coupling and no inversion symmetry. So either non-centrosymmetric structure or disorder alloys, there is no inversion symmetry or interface. The interface is breaking the inversion symmetry. So now the most systems where they are investigated are multi-layer, where broken symmetry broken by the existence of an interface. Typically, a system of cobalt, for example, with on a non-magnetic EV metal with large spin-orbit coupling, so that there is no inversion symmetry for example, this triangle, cobalt, cobalt, platinum. And this induces large spin-orbit coupling. And this is an example of MFM image of one on these skyrmions, down, up, outside, and in the middle is in plane, cobalt, platinum. So in fact, there is two types of skyrmions. If the spin-orbit coupling, the diamond is very large, the ground state is a crystal of skyrmions. But this is not the most interesting case for application. I am focusing on application. With the intermediate value of the DMI, in fact, the skyrmion subsists, the ground state is ferromagnetic, and the skyrmion subsists as a sort of metastable state, metastable configuration protected by the topology. And so these individual skyrmions, particles protected by topology, are the most interesting for applications. In fact, mainly because they behave as quasi-particles. In particular, they can be manipulated, displaced by electrical current, as you can see in these animations. And so these skyrmions are at the basis of many applications that have been proposed. The most known is replacing the hard disk with a fixed information on the disk, and restrict memory, where the information is stored in sort of groups of skyrmions. So each in a given skyrmion, there is no skyrmion or one skyrmion, and the information can be coded by the presence. And there is a lot of other applications that have been proposed. For example, logic gate, where the input current in the gate is not an electron, but is a skyrmions, and so the manipulation is then either duplication or annihilation of skyrmion in the gate. I don't want to describe the complication of this structure. I can say that today there are many work has been performed on multi-layers, where the DMI is induced by the breaking of symmetry, for example, between platinum and cobalt. But of course, cobalt cannot be between platinum and platinum, because now there is no longer breaking of inversion symmetry, but it can be iridium, cobalt, platinum. And in multi-layers, with some coupling between the different skyrmions in different cobalt layers, to have a larger volume of the skyrmion and more stability at room temperature. For example, in this image are 4 skyrmions in this type of multi-layers with a diameter. In this time, it was between 30 and 80 nanometers, and now we can go down to, say, below at around or below 10 nanometers. So, in fact, these skyrmions can be created, for example, the most easy way to create skyrmion in a ferromagnetic layer is by current pulse, because the current pulse around the effects induce the spin polarized current around induce torques and instability of the structure. And finally, after checking a little this structure, what remains at the end is, after checking strongly, what remains is structure that are topologically protected. It is the skyrmions, for example. And this skyrmion can be not only, for example, nucleated by current pulse at a given point, at a given time for device. And they can be detected, for example, by the anomalous Hall effect, because when there is a skyrmions at the cross, in fact, the magnetization is smaller, and there is a difference is voltage, traverse of voltage due to the anomalous Hall effect. So, and the motion is generated by the injection of spin current and the corresponding spin torques induced by the spin transfer mechanism. And for example, flowing a current in this platinum here inject into the magnetic layer this spin direction. For charge neutrality, attract this spin direction. There is, in fact, it can be described as an injection of a pure spin currents, and this injection of spin currents induce a velocity not in the direction of the current. There is a problem. There is some, due to the topology of the skyrmions, there is some angle between the current and the velocity. And so, okay, I don't want to discuss this point, but I can see that the velocity of the skyrmion, or the current-induced motion of the skyrmion, can be very large. You can see in this figure up to 100 meter per second. That is 100 meter per second means 10 nanometer cover in 100 picosecond, a very short time. But in fact, I would say that in the most frequently used structure, that is this multi-layer deposit by sputtering, the concentration of the effect is not small enough. And finally, there is some pinning of the tuning. The skyrmion can be pinned by defect. This is the creep regime with no motion. And then even in this range of linear variation, a difficulty, a drawback of this structure is that the velocity is not really uniform in this sort of multi-layers. For example, I can see an example of the trajectories of skyrmions in this range here. You can see that the skyrmions behaves more or less. This one is more or less linear, but it's not exactly parallel to this one. Some are pinned by defects. And so there is some difficulty to go from, to proceed from physics to device at the moment with this difficulty of having really uniform motion of these skyrmions. So I will say that, and so we have to explore other ways. This is the life of the physicist. And yes, also a way to explore a new way to improve the performance for device or to find another type of physics. And so what I will describe now is the spectrum with skyrmions when one goes from 3D materials, layers, to 2D materials, like graphene. Graphene is not a magnetic material, but of the same category as graphene, van der Waals materials and van der Waals heterostructure. And so, for example, a typical example of 2D magnets is what is called FGT. FGT is a ferromagnetic with outer plane magnetization. It can be prepared, very good crystal can be prepared by MBE, also by CFDs. It can be obtained by exfoliation, like graphene. Of course, because to escape for Mermin-Wagner theorem, that means that if for Heisenberg spin there is no ordering, magnetic ordering, except at 0 temperature, and we have to break to escape from Mermin-Wagner theorem by a strong anisotropy, going from 3D to 2D. If there is a strong spin-orbit coupling and perpendicular magnetization, going from Heisenberg to Ising, there is a ferromagnetic behavior. As you can see, the typical cycles, magnetization cycles of in this sort of compound. At the moment, the ordering temperature are below room temperature, but there is several works recently that I don't have the time to describe, that by proximity effect, the order Curie temperature can be raised well above room temperature. So with some perspective of application. And now, coming back to skyrmions, the advantage of these 2D materials is that you can have the structure with an intrinsic breaking of the inversion symmetry. For example, in this Janus transition metal dichalcogenide, you can see the fact that there is tellurium below, sulfur above, break the inversion symmetry. And this is a calculation we have done before doing experiments. So the inversion symmetry is broken like at an interface, and we can, from DFT calculation, expect large EMI, and also a Monte Carlo simulation leads to the existence of skyrmions, at least at low temperature, because the order in temperature of this one is not very high. It's about 150 Kelvin. And in fact, in this 2D structure, in van der Waal heterostructure, the DMRI can be also introduced by interfacial breaking of symmetry. Okay, excuse me. And for example, by depositing FGT on this D-Shackle-Genide on FGT, and then the DMR that have been introduced by the breaking of the symmetry of the interface induces skyrmion. We can see typical image by low-end microscopy of these skyrmions, typical characterization, or simply by some oxidizing the interface of FGT. For example, in our experiments where without oxidation, by protecting the surface, we have block skyrmions, no induced by DMI, and by oxidation, we have the typical nail skyrmions that are interesting for the application. And the good news also that we had with this structure, with this 2D skyrmions, skyrmion in 2D materials, is that can be displaced by a current in the same way as the skyrmion in 3D structure, you can see. And it appears that because the structure is very perfect, that the motion is more uniform and also apparently is more parallel to the current. So there is a lot of problem to understand, to explain these experimental results. What is the structure of the skyrmions in the vertical direction? What is the vertical profile of the skyrmions? If the DMI is only at the top interface, and what is exactly the mechanism of the motion, but I don't want to consider. I was simply to continue a little more on the speculation we have and the new ways that we want to explore. In fact, by beginning by calculation, that I am collaborating with somebody in China, en Guyane, and with Meyer Schiff in Grenoble. And for example, I present the result of the calculation. We are now proceeding to the experiments on this compound, these 2D compounds, chromium, nitrogen. And it's more or less like the structure of graphene, except there is some buckling. For example, in this structure, you can see the chromium atom are above, buckled above, and the nitrogen are below. And the interesting of this structure, so this is one of the possibilities can be done with these 2D materials, is that by applying a field and reversing, this is a ferroelectric material, of course, because there are not the same charge in the black circle and on the nitrogen here. And if you apply a magnetic electric field, you can reverse from to ferroelectric polarization. It is a ferroelectric material with a possibility of switching easily by an electric field. It's easy to apply a strong electric field with a very thin layer, of course, with a small voltage. And so the system can be switches between these two directions. And what can be calculated also is switching as a function of the electric field which is applied, switching from P down to P up for the ferroelectric polarization. And at the same time, the result is that, in fact, there is also no inversion symmetry in this structure, of course. And there is, of course, a DMI can be calculated, and one sees that one goes from a DMI leading to this state with clockwise chirality to counterclockwise chirality. So this sort of structure could provide a way not only to have skyrmions, but to easily switch from 4 categories of skyrmions with clockwise or counterclockwise chirality, and so also depending on the field, which is applied from up in the center or down in the center. And this is a simulation giving rise to this structure of this common. This common can be relative, according to the calculation, relatively small in this structure, about simply a few nanometer. And okay, so I don't know what if it remains a long time for me, maybe. Okay, I continue, and I will take another example of topological systems. And the topological, the hash bar and topological insulator surface state and interface. Introduction to spin-orbit coupling with topology in 2 dimensions. So you can see the usual dispersion curve of the surface state of what is called topological insulator. Insulator with conducting states, 2-dimensional conducting states with this dispersion curve. In fact, the Dirac cones, it is called a Dirac cones. You can see an RPS image of this cone in one of these topological insulator. And at a given energy, for example, we consider the electrons at the Fermi level here, you have this locking between the direction of the wave vector of the function and the spin of the electron. You can see here, this is what is called locking between spin and momentum. And you see this spin and momentum locking is at the base of interesting conversion between spin current and charge current and vice versa. Some people say also that these states correspond to a new quantum state of matter, because instead of having for each particle 2 degrees of freedom, momentum and spin, there is a single degree of freedom because the spin is locked with the momentum in this. In fact, for application, the same sort of locking between spin and momentum is obtained also with the electron at hash bar interface. At hash bar interface between 2 materials or at surface of a given material, the spin-orbit coupling plus the absence of inversion symmetry introduced by the interface leads to what is called the hash bar interaction, that is some coupling between momentum and spin also. And so finally, this leads to this sort of dispersion curves, and finally to at a given energy, these 2 Fermi contours with opposite locking of spin and momentum in the 2 Fermi contours. So it's more or less the same, except that there is some compensation of this Fermi contour by this red one. And this interesting property of these materials leads to interesting effect of conversion between charge current and spin current and vice versa. This is the Edelstein effect. For example, if a current flows into the surface state of a topological insulator, it means that, for example, the Fermi surface is shifted. There is an overpopulation of electrons on this side when the current flow. That means there is an overpopulation of this spin direction automatically, a depletion of this spin direction on the other side, and finally, if there is another material above the topological insulator, this spin will diffuse into the other material. This one will be attracted for certain neutrality, and this corresponds to the ejection of a spin current. The spin current is always this pictogram I see. Electron, no charge transport, but electron with 2 spin direction going in opposite direction. And in fact, the same effect is expected for hash bar interface, except there is some compensation between this Fermi contour and the small one, the red one. And in both cases, you can characterize the conversion from a 2-dimensional spin currents into a 3-dimensional charge currents by not the same units, of course, by this coefficient, which is the inverse of length. It's a notation introduced by Otani in Japan. So this is one efficient way of this charge to spin conversion that is already used with the spinel effect of material. Spinel effect is also in a 3D materials. The deflection of electron, for example, blue spins up and the down spin downs leads also to the same type of injection of a spin currents. And this is a spinel effect that is already used in some device, which is a SOT RAM, that some MRAM, but where the switching between the two states of the RAM is induced by a current in the platinum layer or tantalum layer above, and by using the spinel effect. Okay, and so in fact, the only difference here, we have also the same conversion between charge currents and spin currents, except that, as we'll see, the efficiency is much larger by 1 or 2, more or less 2 order of magnitude with the Edelstein effect. And in fact, in the application I will present, we are using not the Edelstein effect, but the inverse Edelstein effects. When a spin current, this spin current is injected into, for example, at this on these 2D electrons here. In fact, this that means injecting the spin direction and attracting outside this spin direction. This spin direction can be accumulated on this side. This one will be depleted from this side. That means that this injection of a spin current that can be done, for example, by several techniques like spin pumping, by FMR of a ferroelectric material. This leads to the transformation of a spin current into a charge current, and this can be done also with a Rashba interface in the same way. And finally, there is the usual coefficient is the lambda inverse Edelstein length, which is a length for the conversion from a 3D spin currents into a 2D charge currents is a length. And in fact, and I will describe the application of this effect in one of the devices we are developing with Intel for the new generation of logic device. And in fact, when you have to choose between topological insulator or Rashba, in fact, at first you can say, okay, topological insulator will be better because there is no compensation by two different Fermi contours here. Yeah, but in fact, if you look at the theoretical expression we derive from this lambda, it's not only due, here is the slope of the Dirac cone and the relaxation time is a two-dimensional electron gas. And here the two-dimensional electron gas appears also on the side of the Rashba coefficient. That means there are two coefficients who can have large effect either with a large Rashba coefficient, but also if you have the best result can often be obtained by reducing by a very long relaxation time, a very large mobility in the two-dimensional electron gas. We see, so for example, the best result that we have obtained with electron gas as the interface between two insulators. In fact, having two-dimensional electron gas between two insulators allows to suppress the shunting effects by some conducting layer in addition to the two-dimensional electron gas. And so I will present an example of device related to the collaboration with the Intel company for the development of meso low power logic components. In fact, the two-dimensional electron gas that we are developing in first rank for this structure is not the only one, is the two-dimensional gas as interface between these two insulating oxides, the well-known LAO-STO system. STO-LAO is a Rashba electron gas, and the inverse Edelstein effect can be investigated by pumping a spin current, doing in this layer, in this structure, doing the FMR resonance of the magnetization of this permalow layer. Finally, at the resonance, there is some accumulation of spin that inject below a spin currents and then will induce a charge currents in the two-dimensional electron gas. So that means that what is expected is at the resonance field, an emission of charge current or voltage, or say by measuring voltage, voltage needed to compensate charge currents. So you see typical results of these spin currents with inversion when you reverse the magnetization of the ferromagnetic layer. And so, in fact, it appears that the lambda is, in fact, and the interest of this system also is that it is very sensitive to a gate effect. By a gate effect, you can displace, you can move the Fermi level from this position to this one, and you so you explore different position and different value of the Rashba coefficient depending on the position of the Fermi level, and this is the experimental result. As a function of the gate voltage, you can go from a positive signal, this positive conversion, to a negative conversion. That is, you converse for the same spin currents, you reverse the charge currents induced is a two-dimensional gas. And the good surprise was that these effects are very large and leads to very large lambda of inverse Elchan effects that we come, and even larger results recently we obtained simply by, this is mainly in the group of the experiment by Manuel Bibes in our lab, by injecting also at the interface between aluminum STO, there is also a two-dimensional electron gas. The origin then in this case is clear. In fact, aluminum pump some oxygen in a few atomic layers. You can see the evolution of the concentration of titanium 3+. And so this means this is the origin of the electron gas in 2 or 3 atomic layers here. And this electron gas has even more a stronger efficiency for the production of charge current from spin currents. You can see the typical curves. Again, the lambda can be as large as 28 nanometers or becomes for another voltage by shifting again the Fermi level to something which is also -20. So this is the best systems we have found, and that is one of the materials that we are developing in the frame of a collaboration with Intel. In fact, this the result we obtain as this with this two-dimensional electron gas are at the same level, even larger, that can be obtained with topological insulator. And I will say 2 orders of magnitude above the result obtained with EV metal and the spinel effect of EV metal as platinum or tungsten. And this is the project with Intel, MISO. Why? Because it's used a magnetoelectric effect and spin orbit effects. And in fact, it can be described, okay. In fact, in this sort of structure, the main element is this one. The input voltage is used to manipulate the manipulation of this layer by magnetoelectric effect via a multiferroic material, and then by sending a pulse current through the ferromagnetic material, this spin polarized current is transformed in charge currents by the inverse Elchan effects at, for example, in the LAO-STO electron gas, Rashba electron gas. In fact, the objective, of course, as many objectives in this industry, is to decrease the consumption of energy, and also having also relatively fast computations. And you can see MESO, the objective for MESO is very ambitious as a function of the consumption of energy. And this is related to the problem that you know, how to reduce the total energy consumption by all the technology of information and communication. This is the curves that recording start only. Okay, and then with this, you can see that this is today there are 10% of the electricity production in the world is for all this technology of communication, information, telephones, and so on, computers and data center mainly, and it's expected to increase strongly due mainly to the multiplication of the data center in the 10 next year to have about 20% in 2030. And so you know about this problem of trying to reduce the global warming by reducing all the energy consumption. And you know, this is a problem of the huge energy consumption of the data center, and at your level, you know also what you are consuming when you, for example, we search some site by Google, for example. And so coming back to the physics, so the structure, we are developing this part of the system. And so a system in which a current crossing the ferromagnetic layer, heightened by the first part, by magnetoelectric coupling, will be transformed by this spin orbit material, by this spin orbit two-dimensional electron gas into a charge current and output voltage. And some tries have been already done with this sort of structure, injecting from the magnetic layer into the platinum layer to try also what can be done with the spinel effect, and this gives for the merit factor of this structure this sort of results here. And what we are expecting, what it can be expected is not our job, is the work of Intel with topological insulator, and what we can expect with LAOSTO and ILSTO when we plot the same. This is the function of the equivalent of lambda for spinel effect with the theta spinel effect multiplied by the spin length. And so we are on the way. Of course, we have been a little delayed by the pandemic, but it seems we are again to have a better result at room temperature, but it seems that it will work. And in fact, we have another system, a Dirac semi-metal, so alpha-tin, single, very thin layer of this alpha-tin with these Dirac cones, and we are the Fermi level for the silver on alpha-tin. The other material, silver, is very good to have a Fermi level just close, just at this position above the, in fact, silver is good to have this the Fermi level just at the good position, so on the Dirac cone, but out of the bulk bands, and so we obtain large effects of conversion. And recently we have, because this sample had been prepared by MB, which is not very technological for the industry. And so now we, in collaboration with Oceano State University, we are working on, and with some company also, with alpha-tin prepared by sputtering. And so, for example, this is one of the recent results that we publish. Yes, this time for the charge to spin conversion, so flowing a charge current into alpha-tin to reverse, to inject a spin current into this magnetic layer and to reverse a magnetization. Can be this, can be easily, we can reverse easily at room temperature in zero field, the magnetization of the layer. So this is also another direction of research going to this type of MRAM, SOTRAM based on a two-dimensional electron gas at the surface of alpha-tin. Okay, so it is the end of my, so what to conclude is, okay, we have seen that physics is always evolving. We are managing to study, to explore, and we'll suppose I can continue sometime in this direction. And so I want to thank all my co-workers at Université Paris-Sud, in other labs in France, in Japan, USA, China, and in Brazil. You have seen how many co-workers have been from Brazilian university, and I've been very happy to work with all of them. And I thank you for your attention. Okay.
Okay.
Yeah.
Okay, so thank you very much, Professor Fert, for this inspiring talk. I think we do have time for 1 or 2 questions. Unfortunately, I have to apologize for the connection problem at the beginning, but could not have control on that.
Yeah. No, I did not understand the problem at the beginning. By Zoom, always by clicking with the site, I was going to the meeting of yesterday.
Yes, I think that was a problem from their organization. They should actualize your browser to So you should first actualize the browser, then they will send you to the right site.
So I could go to you by YouTube, but it was not interesting for a presentation. I cannot do the presentation via YouTube. Huh?
Sorry, I apologize for that. But anyway.
Okay, no matter. I've been pleased to. Okay.
Okay.
So you have a question?
Oh yeah.
Please.
All the questions are, yeah?
Angela, I'm Angela Cautal from Federal University of Pará, not in Recife. So thank you a lot for your very interesting and inspiring talk. So my question is concerning your first part of your talk concerning Screamium. And you show some Screamium 2D materials, and some of them you argue that the DM vector comes only from the broken inversion symmetry.
Spin orbit with spin orbit plus inversion, both. You need spin orbit coupling, but in fact,
that was my question, because some of them was only chromium with nitrogen, so the spin orbit coupling is not a heavy material. So where comes the spin orbit coupling that?
Okay, any material has a chromium has a modest spin orbit coupling. But what is important is more or less the product of the spin orbit coupling by the electric field due to broken symmetry. And so sometimes you can, if the spin orbit is small, is compensated by a large electric field. And a ferroelectric material is the best. Okay, you can compensate a small spin orbit coupling by ferroelectricity, because in a ferroelectric material, this is the electric polarization that breaks the symmetry. Okay, breaking symmetry means inducing some electric field. It's the same.
Yeah, I got it. Thank you. Thank you very much.
Okay. Any other question?
Yes, I have a question. If I understood correctly, what you described with the Screamiums are localized structures that you can manipulate.
Yeah.
Yeah. And what the application you showed is a delay line. The same kind of thing, a delay line. So you move it. And so the same thing has been done with optical localized structures at the beginning of this century. And have you ever compared both?
I don't know. You refer to which sort of structure? With the motion of what?
So they have been called optical cavity solitons, which are localized structures in semiconductors, that optical localized structures in semiconductors.
Yeah, no, I don't know this work on optics. Okay, I'm not very good in optics. I'm sorry. No, I'm sorry, I cannot answer.
There was a silly question.
Sorry, yes, okay, go ahead.
Albert, it's a question about name. So it's silly, not about physics. The topological insulator is a material in which, in the bulk, it is insulator.
Yeah.
In the surface, it is conductor. I always thought that it should be called a topological conductor, not a later.
Yeah, the conduction is by the surface, the topological conductor at the surface or the interface.
So the interesting part is the conduction at the surface or interface.
Yeah, and it's better when the bulk part is insulated. Unfortunately, in some cases, there is also some conduction in the bulk, and the problem may become a little complex when we have a conduction at the same time at the surface and in the bulk. Difficult to separate both the effects. So,
okay. Thank you for your great talk.
Yeah, thank you.
It's never too late for you to enter, for us to have a collaboration.
Yeah. Okay.
Never too late.
Yeah. Sometimes I have sometimes I send you some mails, but sometimes I have not the time. Okay, I could ask Sergio what is his advice on these things, but by email is not very convenient. The best will be to be able to personal encounter again.
Sure.
Okay, so I think we should move on, and I really would like to thank again Professor Fert for this impressive talk. Okay, so the next talk will be presented by Professor George Budebs, and I would like to invite also our emeritus professor Cid Araújo to make his introduction. So please.
A last word for me. Bonjour, Laura Steren. Okay, I stop.
Bonjour, everyone. I'll make this introduction to George Budebs. George is a professor at Université d'Angers. His doctoral degree was in 1988 from Université de France-Comté in Besançon, northeast of France. After his doctorate, George worked for 2 years as a research and development engineer in a company in Toulouse, a company affiliated to Thomson. At that time, his research activity was in the field of computer vision. So he designed dynamic illumination of systems for automatic inspections of electronic boards. In the year of 1990, George was hired as an associate professor in the University of Angers, where he started in nonlinear optics, developing new methods for measuring nonlinear materials, nonlinear susceptibilities of materials. Presently, he is still working in nonlinear optics, but he is deputy director of federative research structure at Angers. The name is Matrix. That's composed by 2 laboratories, MOTEC, which is a Unité Mixte de Recherche of the CNRS, and the Laboratory of Photonics. The research has, this research structure has a mission of coordination of the material science activities in the University of Angers. Well, about the University of Angers, I would like to say some words. The university was founded in the century 11 and received the present title of Université d'Angers in the year of 1337. End of the Middle Age, about 163 years before Brazil was discovered. It has about 27,000 students, and the city is a very nice city with less than 170,000 inhabitants. I like very much the place. Since 2003, we have been collaborating continuously in several projects with many visits to Angers and to Recife, and applying new methods of nonlinear spectroscopy to study some glasses, liquids, and crystals. So, well, I'll stop here. It's too long, the introduction, but I'm sorry. I will stop here. And I thank you, George, for accepting our invitation to participate in this symposium. It's a pleasure to have you here today. Please start your presentation.
Thank you, Sid, for this presentation. I'm very grateful to you and honored to be here. I would like to, first of all, express my feeling that it is a little bit difficult to start after Albert Fert, Professor Fert. I will try to do my best with the English. Let me share my screen and let me see at the beginning if you are seeing the screen of my slides. So I should go to Zoom. I should share my screen, which is this one. And I think that it's okay now. Do you hear me?
Yes.
Yes, we can hear.
And the slides also, it is, it's okay?
Yes, yes.
Okay, so first, I would like to thank the organizer for this virtual symposium and for the invitation to speak about the France-Recife Collaboration. 50 years of collaboration. I was not born at that time. Yes, I was born because I was 10 years old, but I used to dream about visiting Brazil at that time. So I will have two chapters to speak about. First, the first chapter will speak about the 20 years of collaboration in the field of, and the second with optical systems and application to certain other nonlinear characterization.
Ok, Rubi, isso vai render aqui.
In a collaboration, you have to take the plane, and the question is, what do you dream of when you go to Recife? Personally, I dream about sea, white sand. I dream about coconuts, good food, and carnival. And that's why the background of the screen that I am using give me the illusion to be in Brazil now, even if it's virtual. But when my collaborator from Brazil come to France, maybe they dream about physics, dealing with the necessary power needed to take off. I think also that they dream about wine, good food, snow, not very much snow, moderate temperature, anyway, to escape from the heat of Recife, and the castle to visit, as the castle Château de la Loire. Anyway, between two meals, sometimes we use to shoot intense laser pulses to produce ultra-fast nonlinear optics. And we never played at this game. Next time it will be scheduled on the program for sure. It's a promise. That's why I will speak now in the second chapter of my talk about optical system and application to third order nonlinear characterization technique. So let me rapidly take an overview of the most significant point and results that we had within this 20 years collaboration. The adventure started with the Capes Coffee Cup agreement in 2003, but I was not able to find the coordinators. Maybe it was André Monteil and Marcel Poulain in Rennes for the French side, and Sidney Ribeiro in Araraquara with Sid in Recife. Anyway, during my visit, I remember that at that time my wife was pregnant and the baby waited for me to go back home, and he was born two days after my coming. It was very good and very kind from him. And my first trip, I was young, and I still had hair on my head, as you can see in this picture. Edison at that time, I see myself now. Do you see the screen?
No, we cannot see.
Okay, here it is. So at that time, Edison was a PhD student, and he was working on that scan. He gave me the opportunity to participate with him in his experiment at that time. And I was initiated to the scan in this visit in 2003. And after we had collaboration between Angers and Recife, the collaboration took place either on invitation by the two labs or in a more formalized framework as a visiting invited professor. A big part of my thematic is developed in close collaboration with Professor Cid de Araujo and his colleague also. I will not forget Anderson Amaral, Edilson Falchao-Filo, and Professor Anderson Gomez. We are writing together a paper now, so we are still collaborating up to now. We had more than 20 articles in common since 2003 in reviewed international journal. I will not list, sorry, it's still there. So this is the list of the papers. I will not go into the details, but I will point out maybe three things. The first one is in 2013, we had an award of a chair for excellence to Professor Cid de Araujo to come to Angers to participate, not to participate, but to initiate a project in a nonlinear spectroscopy for 6 months stay. He came for 2 years, 3 months each time. And the most important result to note, we had in 2013, during my stay there, an experimental setup and soliton observation in CS2 for the first time. It was published in PhysRev letter. And we had in 2016 an invited review paper of 30 pages gathering the results related to the scan and to measurement method in general. It was published in reports on progress in physics. And I would like, before I continue scientific presentation, to thank you for your collaboration over the years. I have enjoyed working with Recife and I have learned a lot from there. Thank you again for your thorough work and the excellence of your research. I also do not forget, Cid, all the invitations in your family. In addition to a collaboration, a friendship has been built, and I look forward to seeing you all in person once again in the future. So I have one more photography to show with Professor Boris Malomed celebrating different types of soliton and their ability to be robust, to propagate straight ahead along several Rayleigh lengths in the presence of strong ethyl absorption. And this is the photo, Cid. I don't know if you remember this photo. Anyway, at that time, going back to the office, we had a hard time writing the paper, but finally it was accepted. So let me now enter in detail my talk. So I will define, first of all, I would like also to apologize for those who were present at my seminar last time during my stay. I will repeat much the same presentation from here because I did not have time to put again the last research that I'm doing now. But it will be an occasion for some of you, if you want to have your break coffee now, go ahead. So I will introduce approximation that it is usually used inside the characterization technique and the nonlinear material, how we define it. I will explain about Mach-Zehnder interferometry, which was the first experiment that I had in Angers. And after that, nonlinear characterization technique using Z-scan inside for F system. And we can finish this outline by a conclusion. I will let you read all the other lines in my outline, but I think that for time it will not be the occasion of all of this to explain, but some of them I will be, it will be possible. So the approximation that we have to use is a low excitation regime, instantaneous response and decay of the material. The nonlinear medium should be regarded as seen. There be negligible no chromatic dispersion. We are in the picosecond regime, and we should assume that the material is defined by linear absorption and nonlinear absorption defined by beta, and the nonlinear index variation defined by N2, which is the main quantity that we are looking for to make the measurement for to characterize the material. Ehrman showed that the output and the input in the amplitude field are related using this formula. If one takes the ratio between the output and the input, we can see that we have, in taking the modulus, the nonlinear transmittance defined in amplitude, the nonlinear transmittance of the material, which is related to absorption inside the material by alpha and beta, and if we take the argument of this ratio, we will have nonlinear phase shifting, which is related to N2, the nonlinear index. To have an order of magnitude of this quantity, let us consider that there is no absorption. And the nonlinear transmittance, in that case, it will be defined simply using this relation. The nonlinear phase, which is the argument of the nonlinear transmittance, is related to nonlinear index variation, which is related to the incident intensity by the coefficient that we are looking for. If one uses a classical interferometer in the visible range with a 1 millimeter thickness, and if we consider that the measurement could be done at 100 milliradian, which is normally 3 times higher than the noise, so we have signal to noise ratio equal to 3, approximately, more than 3, I will say. The nonlinear index variation at the maximum, the peak, it will be 10 to minus 5. If we consider that the material damage is about 1 gigawatt per centimeter square, to compare with the summer shine, which is 10 order of magnitude lower, and the N2 that we can measure, it's 10 to minus 18, which is approximately the N2 of CS2. It's a liquid, it's very nocive, but it is used commonly in order to calibrate the experiment that makes the measurement. So here I will start with the first experiment that we have done in Angers using interferometry technique. It was a Mach-Zehnder technique. If we follow the beam from the entry here, we can see that there is 2 reflections on this beam splitter, which is a glass plate, normal glass plate. One reflection will go to the Mach-Zehnder with his 2 arms, the probe beam and the reference beam. The other reflection will go to monitor the energy for each laser shot. And the strong energy which is transmitted is focused into the nonlinear material, and it is spatially and temporally recombined with the probe. So the probe could read the information that it is written by the pump beam, And with the interference of the probe with the reference arm, by taking an acquisition on the CCD, we can obtain a fringe pattern where at the location where the pump is, this fringe pattern will be deformed. There will be a deviation that could be related to the pump beam. There is an image of the pump beam also, the transmitted one here. And you can see with this prism, we can, by moving this prism, we can proceed to experiment with temporal excite probe 1. But in what will follow, we will adjust the prism in order to obtain the time point 0 of the response of the material. I will show you an experimental acquisition, and we can see here the local deformation. It's very small deformation due to this beam, which is transmitted. This local deformation, it's obtained with high intensity, but generally the incident intensity is low, and the local deformation is difficult to see to the naked eyes. But to obtain the information on the nonlinear transmittance on this information, we use Fourier formalism. We take into account here a Fourier transform of a region of these rectilinear fringes. And in the Fourier domain, we can see that we have normally, if we don't take into account the noise, this 3 point and this 3 point, we have 3 regions where the spectrum is non-zero. The central region and 2 other symmetrical region which are around the 0 of the spectrum. So the information of the deformation here is contained inside one of these regions, because these 2 regions are symmetrical and they give the same information normally. What we'll have to do in order to obtain the information on the nonlinear transmittance is to proceed to the inverse Fourier transform, and taking the argument of this inverse Fourier transform, we'll obtain the nonlinear phase shift, which is related to the nonlinear index variation. And if we proceed to a spatial filtering, the same that has been done for the phase shift, we can have the pump beam also. And if we plot pixel by pixel, the nonlinear index versus the incident intensity, one can obtain normally the N2 value, which will be here showed by data, experimental data. And from the linear regression line, the N2 value is given by this loop. How to obtain the absorption, the beta coefficient 2 photon absorption. Here we can see the fringe pattern without the pump beam. This material is a chalcogenide glasses. It is normally for this composition, it's relatively high absorbing material, but we can have higher absorption than in this material. So we take a fringe pattern, which will be the reference, and we take another fringe pattern with the pump beam. And you can see here there is a decrease in the visibility in the fringe pattern. So this decrease is due to the nonlinear absorption of one arm of the Mach center. So if we take now the inverse Fourier transform and the modulus of this inverse Fourier transform, we can obtain an image of the nonlinear transmittance. And you can see the image here. When it is blue here, that means that the transmittance is equal to 0. When it's red, the transmittance is equal to 1. So after that, this function, which is related to the nonlinear transmittance, the image that you can see here, if we plot this function versus the incident intensity, we can obtain the 2 photon absorption coefficient. Let me say that in this case and in the precedent case, the information is partially resolved. So we have an information about the information, about the nonlinear transmittance. So in this technique, we can obtain the sign of N2, of course, because the deviation, if it's in one side or the other side, that will give opposite side for the N2 value. It is a spatially resolved. It is. It gives the real and the imaginary part of chi3. The sensitivity is typical 20 milliradian, which is approximately the same than Z-scan. and we can have a temporal excite probe experiment, which is not possible when doing Z-scan anyway in the original form of Z-scan. But the inconvenience, the setup is very difficult to align, and there is no simple relation for this measurement. For Z-scan, there is a lot of simple relation that we should use, and they are used normally to make the measurement. That's why it's very popular and everybody uses Z-scan. So the same happens to us, because we had to buy a laser, and the origin of this experiment was 30 picosecond. So the coherence length, it was okay to make the optical contact, but with 10 picosecond for the other laser, which is also in the picosecond regime, it was a little bit more difficult. So I had to make something which is more easy in the experiment. And after my visit to Recife, I thought that maybe inside the 4F system, it will be possible to make this measurement as the original Z-scan. So in order to understand the concept for those who are not familiar with that, we consider a Gaussian beam at the entry of the setup, and this Gaussian beam will induce a Gaussian nonlinear phase shift or a Gaussian absorption form. Not Gaussian, but it will be approximately following the profile of the incident beam. So the phase and the absorption inside the Fourier domain here will filter the spectrum that it is incident, and the autodiffraction of this spectrum will produce a change in the image intensity. So if one considers a spatial filter here just before the CCD of circular aperture, and if we move the sample along the focal region here, we can obtain what this is called normalized Z-scan. And this normalized Z-scan in this system, it's exactly the same characteristic than the Z-scan, the original one that has been published in 1990. There is one point here to say that if we fix a sample as z equal to 0, we proceed to a technique which is called I-scan. It means that we have to change the intensity not by changing the position of the sample, but by changing with the polarizer system at the entry of the setup and fix the sample. There is some publication doing this experiment. And another also remark concerning this lens, it produces a far field diffraction, but at the same time, the advantage of putting this lens when compared to the scan, that it will give us the image of the object at the entry. And in this way, we will have more precise measurement by knowing what is happening at the entry of the object, because the picosecond lasers fluctuate too much in the spatial profile. For the theory, it's very well known, and the theory gives the intensity of the linear image depending on the spectrum of the object and depending on the coherent optical transfer function. This coherent optical transfer function is related to the numerical aperture of the optical system and the magnification. Now, of course, the magnification will be 1 in the 4F system when F2 equal to F1. In the nonlinear regime, we have to add this nonlinear transmittance that we defined earlier, and we normally in the low excitation regime we can obtain an image in the nonlinear regime. So all kinds of objects can be introduced. Why not using a phase object? This object, a phase object that we have fabricated for this experiment, is composed of circular glass plate and on which is transparent dielectric material disc has been deposited here, and this disc has a thickness and index of refraction such that it will retards the phase of the incident light by a quarter wavelength to see the maximum contrast in the image plane. That's what we can see here in this slide. We can see here the linear acquisition with the nonlinear phase shift equal to 0, of course, in the nonlinear material. And in the nonlinear material, if we induce 0.5 for the simulation and consider that N2 is positive, we will have a positive contrast for the phase object. So by considering here absorption equal to 0 for alpha and beta, normally the whole energy should be conserved. And we can see in the case of the red profile here for N2 positive that the energy is deflected from outside the phase object to the inside. And the green profile is the one related to the linear image. And if we have negative N2, we will produce the inverse phenomena. That means that you can see here that the energy is transferred from the inside the phase object to the outside. So the experimental validation is given here for a positive N2 with this material. And you can see here the experimental acquisition with the contrast increasing. And you can see here the theoretical acquisition, the profile of both here. It's a good agreement, very good agreement. How we can obtain this good agreement? By taking the object as the square root of the linear image that is here and adding pi/2 phase shift into the area limited by the deflected border of the phase object. So in this technique, we can obtain the sign of N2 from positive or negative contrast. I should add maybe that positive negative contrast in Zernike microscopy contrast, it was known, but the spatial filter was put in the Fourier plane of the objective. Here we inverse the system, we put a known object at the entry, and in the material that we are looking for the phase, it is in the spectrum of the optical setup. The optical setup is simple. There is more easy numerical simulation than for the Mach-Zehnder, but it is a little bit more complicated than for Z-scan. There is no displacement of the nonlinear material. The inconvenience is we don't have the spatial resolution on the nonlinear phase shift and on the nonlinear transmittance in intensity for the material. And the measurement, if you consider only one laser shot, of course, we will have to do a lot of measurement to be very reliable measurement. So now what happens if we move the sample as for Z-scan? In that case, the linear image that we already saw for Z equal to 0 for a material that is fixed at the focus is no more valid. We have to propagate the field with Helmholtz equation. But it is a little bit heavy numerically to propagate this field. In the space domain, it is better to propagate the spectrum of this field in the Fourier domain. And like this, we can have reduced time for computing, and we can consider with this Helmholtz equation objects without any particular symmetry. And in this system that we are considering, we have 4 propagation to do from the object to the lens, and from the lens to the position of the object, because the object is moving in the focus here. So we should take into account its position. We take into account the nonlinear transmittance of the material. And after that, we go with the optical field up to the CCD. We take into account, of course, also the thickness of the lens, the thickness that are related to the focal length. The image intensity could be calculated, whatever is the spatial filter here. And numerically, if you want to obtain the same result as a photodiode, we will have to integrate all over the pixel that appear in the pixel, that appear on the CCD. And like this, we can obtain the energy taking into account the spatial filter. So I would like to show one more example. Mixing 2 experiments. One is dealing with the 4-wave mixing, because we will consider an object of 3 circular aperture, and the other one, it's Z-scan. So we will combine Z-scan with 4-wave mixing in this experiment. And normally, if you put here a spatial filter with a stop disk in front of the CCD with this circular aperture at the entry, normally you will have no light that will arrive to the CCD. And by the nonlinear regime, we will obtain numerical simulation and experimental acquisition, the same thing, but we will have not only one order which is diffracted, we will have in this case 9 order, but a lot of order also that are less visible, less intense. Anyway, if we integrate over this 9 order and compare the diffracted energy with the one diffracted order, we can see that we have sensitivity of the experiment, which is enhanced by a factor 5 compared to the classical 4-wave mixing, considering only one diffracted order. So in conclusion, in this setup, I hope that I convinced you that it's universal. We can use a lot of experiment that has been considered up to now as different experiment. The nonlinear imaging technique with phase object, Z-scan, 4-wave mixing, eclipse Z-scan by putting here a stop disk instead of a circular aperture, I-scan, multi-wave mixing, and so on. Okay, but we had finally to optimize in order to obtain the highest sensitivity with the highest signal-to-noise ratio. Of course, when you are doing eclipse Z-scan, we have a very high sensitivity, but the signal-to-noise ratio also increase. So the signal-to-noise ratio, but the noise also increase. And the signal-to-noise ratio remains the same with the high sensitivity. How to optimize and to find the best object and the best blocking or transmitting disk here. So instead of the original Z-scan method, we will use what we call D4 sigma Z-scan inside the 4F system. Let me explain rapidly the concept and some characteristic. Here, we will have to perform not energy measurement with a photodiode or CCD, but distance measurement using the CCD instead of the intensity measurement. And it will be more accurate by measuring the distance. We measure the relative variation of the beam west, which is on the CCD. You can see here the transverse section of the CCD and the linear regime. We measure the beam west in the nonlinear regime because of this moving of the sample at the focus. We will obtain maybe broader or narrower beam. And if we normalize and we calculate the beam west relative variation and we plot this versus Z, we obtain a signal which is similar to Z-scan, but it's the inverse of Z-scan. So how to measure this? We have to take into account the first and the second moment of the irradiance profile. Not only the measurement is more reliable with this moment profile, but also the calculation of the centroid will follow the beam, because the beam from one laser shot to another, it's moving. Sometimes it creates a lot of noise. Another advantage for this technique is it is very useful when you have highly nonlinear material. Here I have a calculation glasses with a very big high coefficient, 2-photon coefficient. And the N2 also is very good, the nonlinear index coefficient. And you can see here in the same, for the same intensity in the same experimental condition, you can see the beam west relative variation profile and the Z-scan profile. And you have the same signal, so the same sensitivity. But there is no need to divide the two different profiles to obtain the nonlinear response, because with Z-scan, when you have high nonlinear absorption, you have to make one measurement with the first profile, closed aperture, another measurement with the open aperture, make the division that will increase the error by 2. The pulsed laser, if you look and you make a magnification of the centroid, you can see that it's unstable, the impact of the region. And this instability will follow the center of the beam, aiding additional noise to the signal as with hard aperture. as with the original Z-scan, we use hard aperture. So when we also use the beam width relative variation, physically it's normal to use all the pixels inside the camera. So all the information comes to you without obstructing or deleting some pixels by putting a disk or something else in order to obtain the highest signal with less noise. I don't know if I have much more time. If I can continue, please.
Unfortunately, we are running out of time, but so you
Okay.
have 2 or 3.
Okay. I will only explain this technique and I conclude after that. So, and this another technique has been used combining dark field microscopy with Z-scan method. The principle and is to use object with annular shape. We focus this object into the nonlinear material. And in the linear regime, you can see with the red line, it is blocked by circular aperture just before a lens that it's making the image of the nonlinear material into the CCD. So in the nonlinear regime, there will be diffraction everywhere, and one part of this diffraction will go into the center of this circular aperture and image it here. So we will have images of the nonlinear phase shift, which will be normally very contrasted. And that's the case. In that way, I will go fast here. It's not very important. Okay, that's the acquisition when you can see the specimen as z equal to 0. And we have done measurement with this technique, the same intensity for two different material. It was porphyrin with positive and negative N2 compared to CS2, which is a reference. And you can see that it's very sensitive, especially for absorption, very high absorption, linear and nonlinear absorption. The inconvenience of this technique is that very difficult to align because we have to center the magnifying lens, imaging lens with the circular aperture. It is difficult to distinguish the sign of N2 for highly absorbing material. If I come back here, you can see that the negative and the positive here, they are separated only by a few distance in the Z-scan. But their sensitivity is improved by 2 orders of magnitude, and we can have a signal which is non-linearly natural signal, non-linear natural signal of refraction. So we have characterized a lot of material, different wavelength, and actually I'm working on a thermal characterization because there is something I think that it should be explored in this domain, and in 2D material also I'm interested by that. So the principle of different technique for nonlinear measurement, here is the conclusion. That's what I showed in this talk. The main part of the image processing method, the numerical simulation, experimental acquisition advantage of each technique has been pointed out. And I would like to show one more image, and that's all. That was in Fosti, Iguachu in May 2018. And in this photo, Sid was showing me the way how to be smart, intelligent, and famous. But there were many books to read there, a lot of books. I'm still waiting to finish some of them. And especially, I'm still waiting to be able to come back to Recife to collaborate again in person with the people there in the physics department and face-to-face with everybody there. Thank you for your attention.
Okay, thank you, George, for your talk. I just want to say that we are really running out of time. So if you have a very quick question, then please do it. cannot see in the raised hand.
Okay, anyway, you can have the slides and you can have.
Okay, that would be nice.
And if you have any question, you can contact me. My mail is on internet. You can find it at University of France.
Okay, and also you can leave your question on the chat.
Of course.
Okay, thank you again. And then I think we should move to the next talk, which will be presented by Daniel Bloch. And I'm also very pleased to introduce Daniel, an old friend of mine and also a friend of many of others colleagues here in Recife. Daniel is a director of the research at CNRS. He works at the Laboratoire de Physique de Laser, Université Paris-Nord. And he has received his PhD from the same university, Université Paris-Nord. And as I remember, I think it was still in the old French educational system where one had to work much harder to get a thèse d'état. Okay. I want to also mention that at the beginning of his career, he was awarded the prize Aimé Cotton from the French Physical Society. And I'm not sure, but I think this was a recognition of his great contribution to the field of optical phase conjugation via four-wave mixing. And now you see he changed completely his interest in research in physics, and he is more dedicated to investigate atom and surface interaction. I also want to mention that Daniel has a long history of collaboration with Recife, and he has been the coordinator of several CAPS-COF projects. He has also supervised several Brazilian PhD students, so he has really a close connection with us. So it's a pleasure, Daniel, to have you here today. So please have the screen.
Thank you very much, Tabova. It's a real pleasure to congratulate the 50 years of the Department of Physics. Thanks a lot for all the organizing committee. Well, Tabova yourself, but also all the other people. And it's always a pleasure to see friends that I have in Recife and Brazil. And I would like that we try to share the screen if possible. Is it possible to share the screen?
I cannot see yet your
presentation. Yes.
Okay.
Yes, I think we are good now. Yes. Do you see my screen?
Yes.
Good.
Yes.
Excellent.
Just full screen.
Yes. So
I see the fourth.
Yes. Yes.
Okay. Thank you.
Is it good now?
Yes. Yes.
Good. Okay. So it was needed to have a title, I think, and so I have to choose a title and say how the sabbatical year of Rios Leti at Berkeley in 1982 was very fruitful for us and other stories. And in some sense, it will explain how we shift from nonlinear optics to surface physics, as you explained it, Tabova. To start with, I do not know if all the screen can be seen or if the top is missing, but among facts that I've learned from Brazil and Brazilian people, I will start perhaps very strangely by saying that the first time I've heard about Brazil was I was just a new teenager, and I had an opportunity to watch Brazil-Italy. And mentioning that some kind of World Cup is very strange for me because it's probably one of the only 10 plays of football among my whole life that I have watched on. After that, I would rather skip my interest for cinema novo or for Dona Flor, which happened in the 80s. And to my connection with Brazil, I will go first to 1982 with Jesus. And in Jesus, I had a Brazilian roommate for half of the time. And this roommate actually was Fernando de Oliveira, who came in 83, 84. And I spent only a fraction of the PhD, but I noticed that it was paid by Brazil, which happened several times. And I had to help him for a move-in. And he had a guitar, and he said, "Oh, I'm Brazilian, so I play music, but I do not play football." So it was my first type of encounter with Brazilian people. And in 1985, Rios came to the lab, and we had started to have strong cooperation, self-oscillation in four-wave mixing, and the phase conjugate laser oscillation was described by him and by Marcel too. And I started a long friendship with various people from Brazil. Sid came also in these years and contributed also to four-wave mixing and multi-wave mixing. Tabosa, yourself, you came by the end of 86. So we worked together for 3 months after I left for some kind of sabbatical. And by the end of 87, I met with Marco Soria, who was at the lab for a PhD. And so it was the start of a very long and fruitful cooperation. And my first stay in Brazil was in 88 in the frame of the CNRS and CNPq cooperation. My tour includes 3 weeks in Recife. And among the notable things in this 3 weeks in Recife for the first time, I've heard a seminar in Portuguese. I could understand the 5 first minutes, but it was the first time I heard a seminar on chaos, and it was delivered by Sergio Rezende. The other thing I can note is that as a result of this visit, there was a joint paper with Rios on multi-wave mixing calculation on SF6, which was a molecule. And this was my only way to have work on molecules, at least in the infrared. And as Tabosa has mentioned, I had coordinated 3 times a capascopic cube agreement, always with Recife and usually with Paraíba too. I would say that 1/3 of my papers are with Brazil and more than 40% probably with Uruguay, where we now have an international CNRS lab. And also in the capascopic cube, it was interesting to have extension also not only to LPL in Vitaneuse, but also to Nice and Lille, and then to Aimé Coton and LKB with so Laurence Prévost at Aimé Coton, but also Julien Laura and partly Claude Fabre at École Normale. And among the people who have worked even at PhD level, there was, well, Martin Chevrolier, who was French at the time. We had Pedro Chavez for a fraction of a sandwich PhD, Thierry Passera also for a shared thesis, or partly with Paraíba, and quite recently, Giancarlo de Aquino Carvalho. So it was impossible for me to have a picture because I do not want to have personal picture on the web. But at the time of the real meeting, I can remember that people have said, how is Mr. Bloch in Rio? And this was at the final meeting of the CNRS-CNPq cooperation in 96. So to go more into what I've called to be the title, I have found this joint paper between Rios, who was in sabbatical and already at Recife, and the group of Ron Chen in Berkeley. And what I would like to notice is that it was a paper on optical second harmonic generation. So this looks to be nonlinear optics, as would say usual, but there was some kind of local field enhancement. And this was on surfaces of essentially silver, which has to be prepared. And it was really pioneering work, both in nonlinear optics to increase efficiency, but also to play with surfaces. And it could be probably recognized as a very early work on plasmonics and even nanoplasmonics. And so I've said that this stay of Rios or discussion of Rios, but also on this topic was very important for us. I can quote this paper, which has been already quoted, where you will see that there is, of course, Marcel, Rios, Sid also. And this was a paper on evanescent wave spectroscopy. And this is Doppler 3. So Doppler 3 means that when you go to spectroscopy of gases, for people who would not be familiar with atomic physics, for thermal gases, you have molecular motion, which is a reason to reduce the resolution. And the first thing that you have to do is to fight against Doppler effect. So Doppler 3 was natural. But for this paper, which was a beginning of work with close to surfaces, the student was Pierre Simoneau and Gilbert Grimbert, that we've talked about, and the late Gilbert Grimbert was in the PhD committee, and he has this very good question to Pierre Simoneau. How did he get this idea of playing with evanescent waves? And the very honest answer of our student was, oh, ça c'était des discussions entre les chefs. I mean, there was big discussion between big bosses. And I was still, well, I was permanent, but still a rather young researcher, and bosses were essentially the discussion between Marcel and Rios. And to give an idea of this discussion, I can also remember that the book of Ronchen was often quoted. It was published in '84, and Ronchen was a specialist of nonlinear optics, as you can see on this book. And the interesting part of the discussion was that for this kind of edition, among the first editions of this book, the image here came from a figure of a paper published in Cicero Letter with Ezekiel, Ducroix, and Molo, published in 1977, after Marcel has left MIT and was already considered to be in Villeneuve. And so, reading again this paper, which was, well, seminal for our interest in optics close to surfaces, here is a fraction of the conclusion on it. And so, on the top part in blue, you can see that we said that measurements are essentially the distances which are 100 nanometers to 1 micron, so it's, well, comparable or fraction of an optical wavelength. And two remarkable applications should be mentioned. So one is about the atom wall collisions, which is some kind of short-range atom surface interaction. One is the idea of measuring atom sticking time. This point it started to be developed in the thesis of Marcus Soria, and this was also presented by Martin Chevrolier in further work in Paraíba, and also to play about angular distribution of atomic velocities by the surface. The idea that you have transient response, and between for atoms that leave the surface, this is an idea that was already presented by Martial when explaining about selective reflection. And the second point was more about long-range measurement, that you can expect to see frequency shifts, which would be a signature of long-range interaction. And finally, on the top of the right part of the picture, the last sentence says, these phenomena might be enhanced in three-level spectroscopy of large volume Rydberg states, notably the ion dipole. And I can say that presently there is a contract by the National Agency of Research, which is headed by, the contract is headed by Athanasios Laiotis, to look on these quadruple terms. So this is a very recent activity, while this was, well, one of the ideas was mentioned more or less at a long time ago. So to go now more to an outline of what I could say, I will start with gas cells and Maxwell-Boltzmann and how atoms can fly parallel to the wall. I will go to some ideas of thermal near field and atom surface interaction, other idea of 3D confinement and replacing opal instead of replacing flat surface by opals, and also some ideas about orbital angular momentum, how it interacts with a single atom. So in terms of the general technique to observe sub-wavelength confinement, we have already mentioned the evanescent wave, which occurs when you are at an angle which is above the critical angle, for example, with a prism. In this case, the wave vector is parallel to the surface, and this means that to get Doppler suppression, you will need to have two counterpropagating beams, and this was the idea of the optics.com paper of '96 that I have described. Alternate technique can be just to look on the reflection and the normal incidence. In this case, because this is a reflection, the information you get is not that much on the long depth of the cell. This is rather related with one optical wavelength for one optical wavelength with divided by 2 pi. So you probe typically 100 nanometer. And alternately, if you can fabricate a thin vapor cell, just like here, so the distance can be initially between several tens of microns, but also you can go below 1 micron even to something like 100 nanometer, and that your normal incidence, the wave vector is perpendicular to the surface. And when you have a moving atoms that move not that much along this wave vector, these atoms, they are not sensitive to Doppler effect, and you build up a natural sub-Doppler technique, even just with one beam, which is even with a linear technique. So if you go to a thin cell, what happens is that if you are dilute enough, you travel from wall to wall, and you have a longer interaction time for flights that are parallel to the surface, and you can build up the interaction. So for transscientific, this is much better. Now the point about why to question the Maxwell-Boltzmann distribution. There is here some history in this paper by 1985 by Comsa and David. And Maxwell-Boltzmann, this is old ideas, especially quite old about the surface, which is an ideal surface. So the idea is that usually you have a fraction of the atoms that stick onto the surface and a fraction that will just specularly reflected, which is a rather strange idea. And what is said is that the statement was not challenged for many decades, and that it's not very well known. So why is it questionable? You have the kind of Lambert's law from the surface. You have a cosine theta flux law for ideal gas, but this law is not imposed by desorption. And rather, you can have, planarity issue, local roughness, but also we will see that atom surface interaction can accelerate through van der Waals attraction. It can accelerate the atoms. So there's no reason to have the isotropy that you expect from the Maxwell-Boltzmann law when you are very close to the surface, and especially when thermal velocities are several hundred of meters per second. One can wonder, would it be possible to have atom at a grazing incidence where normal incidence is only 1 meter per second or 0.1 meter per second? And there was only a single historical test of the cosine theta law. So I do not want to go into the details, but because we do not have genuine results, but we try to implement an experiment in Bulgaria with using thin cells. The idea is that we will probe at the center, and we will have, we can vary the distance of this circular pump, and we will see if atoms are able to reach the probe region. And so here's the kind of thin cell which is used. And with some optics, you can move here the position of the cell, and then you will change the position of the pump beam, which is some kind of a ring. And just so in the paper which was published, I will go directly to the referee comments. All of them said this is interesting, but for this is not sufficient because this is heavily limited by technical features. Indeed, the experiment was in Bulgaria, and we expect to have a next generation of experiment. But what was very satisfying is that one of the referees mentioned even that it should be seen as something of a surprise that the Maxwell-Boltzmann distribution is not violated in these experiments. It's just because we do not have enough precision, and rather, this is standard only for velocity of the order of 6 to 10 meters per second. But if it would go below, I still accept something else could happen. So next topic I want to discuss is about the atom surface interaction, which Marcel has explaining what is the van der Waals regime, which is sometimes called also Casimir-Polder interaction, because Casimir-Polder is the same thing, except it includes the retardation, while the pure dipole-dipole coupling in the London model in 1932 was more with instantaneous things. So now that Casimir-Polder is a paper of 1948, but it took quite a long time, about half a century, to have precision experiments, both on the Casimir effect between two surfaces and for Casimir-Polder interaction. And I would say that nowadays, Casimir-Polder wording encompasses the short-range van der Waals regime. So our measurements are often estimation of just of the C3 coefficient in various situations, as you can see, and as it was more detailed in the Marshall talk. And you can see here the name also of various people: Oria, Chevrolier, Feilace, Papageorgiou, and first Athanasios Laliotis, who, when he started his work here. What we used to measure C3 now was to try to see what is the effect of temperature, and more precisely, what happens when we go to the thermal near field. The idea is that blackwater radiation is incoherent and very well known at the origin of photon quantization, but at the turn of the century, people like Jean-Jacques Greffet have been interested in effects of the near field of blackwater radiation, which is very different. This is strongly amplified at small distances. Thermal field starts to be coherent in the near field. It is not at all broadband, colored by surface mode, and it can be coherent emission. This Nature paper, I can remember that there was a long discussion, and Rios essentially explained to us what was behind. At room temperature, the typical wavelength is 50 micron, and if you go to high temperature, the wavelength is shorter. And it has been a ground topic since the nano era for this century. So to explain in some sense the idea, we can go to this 2000 paper by the group of Greffet, where you see for silicon carbide some predicted emission at large distance from the surface, which is nearly broadband with some absorption. But when we go much closer, even to something like 100 nanometer, then the surface is actually emitting just as quasi-monochromatic. And this can be explained by amplification at a short distance, but also by evanescent wave, again, contribution, which are negligible at long distance. So looking on our selective reflection technique and measuring C3, if there would be no atom surface interaction, this would have been the transition on cesium that we would look. This is Rios again, who asked, please show what happens without van der Waals interaction. Here you see the shapes are very different, but when you change the temperature of the surface, not the temperature of the atomic vapor, there is a change which is quite notable, which was sufficiently interesting to be published in Nature Communications. And for these things, there was a communication by the Société Brasileira de Physics before the communication by CNRS on this, because Thierry Passerat was one of the co-authors on it. And I will skip the discussion of the artist's view, which was proposed by SBF, but which for me is not very useful. And so in this kind of idea, we are now trying to investigate on the nature of the surface interaction. Marcel has presented transition on the repulsion which was a work with Ross Feilace, the coupling between two atomic levels of cesium with a resonance sulfide. And we are just doing the opposite now. So it's the reverse transition, which is emission, we want to absorb the thermal emission. So we will be with a hot surface, and the atom will try to absorb virtually and to have modifications. And this will occur only for one of the fine structure of the 7p level, because this is strongly coupled with the sulfide resonance. So what happens is you can compare the two transitions at rather low temperature or much higher. You see that the C3 has strongly increased for the resonant coupling, and the line shape changes, and the change is much more modest and corresponds to decrease when you go to the other coupling. And this has been the work of João de Carvalho, and we hope to have a good paper with it, which this is still underway. The results of the C3 with temperature shows that we cannot only consider the quantum thermal effects, but what happens is we have also to consider the broadening with temperature of the surface resonance. And for that, we went to specific measurement of emissivity performed in Orléans. We see that emissivity of sapphire depends on temperature. From this, after hard work, we can go back to the bulk permittivity. And all this is not at all at the same position at the surface resonance. And we see here the surface resonance with in its real and imaginary part will depend on temperature and will be broader and shorter. So we start to have an atom as a detector of the surface resonance. And for the surface resonance, I said the bulk value is important, but this is essentially connected to the permittivity to epsilon minus 1 over epsilon plus 1. If it is planar, for a theory, it will be different. But if we go back to ideas with Shen, it will be rough surfaces and something different. One of the possibilities that would be of interest would be with this kind to use in the near field the thermal emission to be something like a spectral lamp. And for example, if we remember that silicon carbide emits at 10.5 micron, we can set that SF6 is absorption and at the same wavelength. And it could happen that we could have a population only by thermal surface modes, which would not be the same thing as the broadband Boltzmann distribution of thermal vibrations. Now I would like to go to another topic more connected with the four-wave mixing. I had my postdoc at Bob Hellworth, and he was not at all with atomic physics, but he was a visitor in 1990 and started to have discussion about processing of optical correlation with an atomic vapor. And one of his goals was that it would be interesting to have lambda cube voxels. And there was also nice as an author of this paper who has the same year has the first demonstration of four-wave mixing in a 10 micron cell. And thus remembers that in '89 with Marco Soria, we started to go to a rather short cell, a 1 millimeter cell, just to improve the overlap in nonlinear optics. But also we realized because of the sticking time at the wall that about half of the atoms in that 1 millimeter cell were stored onto the surface. And so we went to the idea of what happens in 3D confinement with these ideas of lambda cube voxels. And this was the reason to turn also to try to infiltrate opals. I think that I'm running out of time, so I will not go to a lot of details on that. But it's possible to prepare with photonic crystals. You have a special role for first layer. And it was possible to see a subdoppler structure for cesium vapor infiltrated in the opal only for some incidents. And the problem is that the understanding is very complex because you have a light propagation from nano-optics, you have transient response, and also to sum the response over this difficult spheres. But if you go to first layer, you can have some kind of, crystalline optics because you have some kind of specific orientation. And we could dream now of replacing soft chemistry of the opals by some kind of periodical etching and to have something more or less equivalent, to have controlled randomization, as you heard by Arturo Lezama. This idea of 3D confinement in random media is what happens in Uruguay. And the last topic I want to mention is, of course, I would say this idea of orbital angular momentum. It started with the fact that there is big activity by Tabosa playing on the four-wave mixing and storing orbital angular momentum in atomic medium. And so sometimes there is a claim that it's possible to transfer the orbital angular momentum with some delay to the atomic medium, and the question is how it is transferred to the atoms. And especially one of the interesting questions, I think, is what happens for L equal 2? This looks to be, to me, rather paradoxical if the orbital angular momentum of 2h bar can be transferred, for example, to a single atom. Is it a collective effect, or is it all to problem of atoms and photons, or only atom and photon? We play with linear spectroscopy. This is usually better. This image, which in some sense explain what will happen, this has been, this is Rios who explained to me finally what happened, which is that you have a transfer of the degree of freedom to external motion, not only to internal degree of freedom, when you are not on the axis. So it's a transfer for the ensemble of particle. And what happens for this cooperation was that the interesting thing was to look what happens for a quadruple transition. If you go to a quadruple transition or a magnetic transition, Klimov from Moscow was involved in this work. He had with Marcel Dutoit joint work already on a quadruple transition close to surfaces and some way to calculate the magnetic field. And what you see here is that for an extremely focused beam, this is the Klimov calculation of the structure of the beam at the waist. You have also you can have non-longitudinal component. But what happens is that what you should see is that at the center, like the E distribution has nothing. But what was very strange for me was that the magnetic field was not at all zero. And if you have a magnetic field which is not zero, then this means that E and B do not overlap. This is actually not a surprise, but for a lot of opticians, we just say, oh, E square plus or C square, B square, E square is only important. Actually, this difference between E and B is crucial for nanophotonics. And this is why if you have a quadrupole or magnetic detector, the Gaussian beam could look different, and it could look to be bright at the center. And it was also a reason for our rather recent cooperation with Japan, notably with Satoshi Tojo, which in 2004 published something with evanescent fields showing that there is an absorption enhancement for quadruple transition. And I could even remember that in the early 90s, when we started work on evanescent wave, Michel Leduc, who was also a visitor in the came of CNRS-PQ, she passed to us in Viltaneuse a question of a researcher from Brazil: is the strictly forbidden 0-0 transition possible with evanescent wave? Well, I still don't know, but nearly forbidden transition, they can be allowed with evanescent wave for clear. There was also in this cooperation with Japan some things with nano-optics, where the funny thing is that this is non-resonant physics. This is only in air for a long time, low power, but close to a nanostructure. And what can be realized is that it's the magnetic structure which happens when the light reflects on this nano-optics, that the B field allows local oxygen dissociation, and then this allows a smoothing of the surface. So just to go to a conclusion, one of the questions often heard about selective reflection is why you play always with atoms and not with molecules. And Rios Leite was not at all the last one to ask the question. And so the standard response is lines are much quicker because they are distributed on several levels. But the molecule surface will be a rich situation. Linearity of selective reflection makes molecules in some sense less bad than what it is for nonlinear optics. And we have quite recently, in an experiment led by Athanasios Lailotis, we could succeed in probing with selective reflection molecular transition. So just to conclude, because I have probably finished my time, I would say that among things that I love in the Department of Physics in Recife is that it is in some sense like a sabbatical. And I can remember, for example, this talk I could give in 2012. It was asked to me, oh, Daniel, can you give a second seminar? Second seminar, I have said, well, nearly everything that we had. So it was a way to present silly ideas. And this is, I think, something very important to have open discussions. And this is one of the things I love very much. So muito obrigado to Department of Physics. And also many thanks to all people that I had the chance to work with in LPL, Marcel Dutoit, Athanasios and Isabel among permanent people, Biplab Dutta and Guadalupe Garsta now in younger students or postdocs. And also we have other cooperation with Orléans, with Bordeaux for operas. With Brazil, I think that I have already quoted most of the actors at the different institutions in Uruguay, Horacio and Arturo, in Bulgaria, Petko, Klimov and Tojo Yatsui and so on. And previous PhD like, of course, João, but also for the operas, Elias Moufarej, Philippe Balin, Gabriel Dutier, Stéphane Briolo. So thanks a lot for your attention, and long life to the Department of Physics.
Thank you very much, Daniel. Nice, very nice talk, very complete and very, very clear. So, although we are out of time, let me say that I'll extend the coffee break. So we have time for questions. Is there any question?
Yes.
Please, Florence.
Yes, Daniel, thank you very much for the talk. Okay, I have a question about the range of the wavelengths you use for the evanescent wave. It is always in optics, okay? And do you plan to have some application in another range, for example, to test the idea on Rydberg atom or something like that?
Well, there is presently some ideas of playing, well, either with selective inflation with Rydberg atoms or also with thin cell. I would say probably rather than with evanescent waves. Well, for evanescent waves, we have to build up the cell, and it's not that easy to have, depending on temperature when we play with cesium, it's not that easy to play with, to have a prism. I remember at the beginning of the thesis of Gabriel Duquier, we had a lot of problems trying to play with this thing, but this is just technology. Now, when you go to near field of thermal emission, when I was saying that the near field corresponds to evanescent waves, what happens is that this is rather evanescent waves, which are at all, well, at all the nearly monochromatic wavelength of the thermal emission, but then it is rather something that is at 12 micron, for example, for sapphire, so it can go to a totally different range, and it could be also considered with the molecule experiment was on SF6 and NH3, the one which was recently published, so wavelength at 10 micron with QCL, and so there's no peculiar limit to the range for optical evanescent waves.
Okay, thanks. My question was connected to quite a lot of experiment when they do a Rydberg atom through EIT in a cell and in nanocell, okay? And then this Rydberg atom can be close to the windows and perhaps will be very sensitive to the effect.
Yes.
Okay. It was the context of my question.
Yes, okay. Well, I fully understand it, and I would say that there have been in the group of Arturo and Horacio in with the random media, that where rather the glass volume is more something like 10 microns or sometime between 10 and 100 microns. They've been able to observe Rydberg levels, and they try to calculate what is the effect of the interaction. And in the same sense, you have the Tillman-Fau group, who has worked with Hole fiber or photonic fibers, and in their sense, you have to go really to the nanophotonic structure of the wave to see what happens, and also to the surface modes. There are interpretations of Tillman-Fau about the surface modes in the optical fiber, and I would say I do not believe at all in what is mentioned about couplings, but this is obviously a very difficult topic.
Thanks.
Okay. Any other question? Well, if not, I think we should go to the coffee break. As we are delayed by about 25 minutes, so I propose to restart the second part at 12:45. Okay?
Thank you, Daniel.
Oh, thanks, yes.
See you.
Yeah.
Após o link, pode continuar aqui, né?
Oh.
Alors. Salut Daniel, c'est bien, tu m'as laissé un peu de moments orbitaux. Tu m'entends? Daniel? Daniel, tu m'entends? Daniel, tu m'entends? Non. Il n'a pas son casque.
Robin? Bruna?
Oi?
Bom, agora já passou o tempo. O Robin Kayseg gostaria de testar a apresentação dele, mas eu acho que não vai dar mais para fazer isso agora. Tudo bem. A gente arrisca.
Ela botou assim.
Can we commence, Laurence?
Yes. Okay.
Sandra?
Yes.
Okay.
Okay.
Okay, so let's start this second part of our symposium, second last part of our symposium. And the next talk will be given by Laurence Privot from Laboratoire Bécoton. And I have the pleasure to invite our colleague, Sandra Viana, to do your introduction. So please, Sandra.
Oh, hello. Good afternoon, everyone. I am present to introduce Laurence Privot. Laurence is a research director at the CNRS, University of Paris-Saclay, associated to the Amécoton laboratory. She obtained her graduate degree at École Normale Supérieure in 1988, and her PhD at the University of Paris 11 in 1990. Laurence works with quantum optics, optical vortex, orbital angular momentum, cold atoms, and photo association. Her first visit to Recife was in 1992, and she started the collaboration with José Tabosa in 2011, already under 2 CAPS coffee cup projects. I met Laurence during her visit in 2011, when we discussed some ideas that may be the motivation of a new project, I hope. Oh, Laurence, thank you for accepting our invitation for this symposium. Please.
So thank you very much for the introduction. So I will perhaps put my presentation. Okay. So is it okay for you? Yes?
Yes, yes.
Okay, okay. So first I will say I thank you very much for the invitation. I am really happy to participate to the symposium, okay, and very happy to be with you, even we are far, but even happy, okay. I will try to retrace here the scientific way that drive us today to for wave mixing in atomic vapor with optical vortices, okay? And just before, oh, it doesn't work, okay. So just a word about the picture I have put here. It is a falling maple fruit. It is, according to my opinion, a pertinent image for the, for vortices, optical vortices, as we will see after that. Perhaps I can skip this slide because it was just to show where is my lab and some word on Paris-Saclay University, but I think that all the people know that. As an introduction, I give here the abstract I gave to Tabosa, and in which I have highlighted some word, and this word will be the key word of this talk, and will define the outline. Optical vortex, orbital angular momentum, quantized, Recife pioneered, orbital angular momentum and for wave mixing, and I will end with orbital angular momentum, entanglement and quantum simulation. So the outline I have defined. I have skipped the four-wave mixing basis, since everyone here knows about that. I will start with optical vortex, orbital angular momentum, and continue with this. In the middle, I have put something on the progress in phase shaping, because it's important. It is okay to develop now a lot of experiment in these topics. So vortices concern many fields in physics, from the fluid, okay, to magnetism, but in a large range. They are related to a spiral form, to a special topology, or also to turbulence, or a curling vector, and very often to a singular point somewhere. Okay, so in optics, the optical vortex is a laser which propagates with a helical phase, a helical wavefront. Okay, and at the center of the vortex, there is a topological point, in a sense that where the phase here is not really defined at the center. It is also called singular beam. So the first idea about optical vortex appeared in 1989 in a paper by Pierre Coulet and his collaborator from Nice. Okay. After that, the properties has been developed a lot, and in particular, I have more time to describe all the things. In particular, two of them. So the intensity of such a beam is a ring of light, and the Poynting vector associated to this vortex is twisted, and he has an azimuthal component, and then it is the reason why we have an orbital angular momentum. And this orbital angular momentum has the value h bar L per photon. L indicates the branch, number of branches of the helix, and the sign of L, the handedness of the helix. So TRM is known to be the third momentum of light. The first one is the h bar k, due to propagation, the continuous value. The second one is the polarization, the spin angular momentum. The third one, the orbital angular momentum, with a large range of value. This idea comes from Allen and collaborator in 1992. If you want to have an overview of that, I recommend this special issue with a lot of mentioned about the application from optical manipulation, imaging, quantum optic, and optical communication. Okay. So it is a quantum variable because it gives a basis for encoding in communication. It allows to do a superposition of state of Rohalem, storing, restoring, transmission, entanglement, and so on. Okay. But the key to do that is to understand the interaction with the medium. So just to motivate a little bit your attention, okay, to my presentation, I show you here some superpositions of orbital angular momentum, okay, and the associated funny pictures. So here you have superposition mainly of 3 angular momentum. So now I will come back to the pioneer experiment with OM at Recife. It was in 1999, okay? with an experiment of four-wave mixing in the cooled cesium atom, where one of the input beam carries an orbital angular momentum with a charge equal to 1. Okay, and you see here at the center the scheme of the mixing of the setup, and on the right here on this picture, you see the input beam intensity, which is a ring, the output one, also a ring, and the signature of the OIM. Here it is an interference between a Gaussian beam, which is a slightly focused, and the vortex. It gives this form with spiral form, and this spiral form is the signature of the orbital angular momentum. In this experiment, the vortex were prepared by a mask, by applying an amplitude mask. Okay. It was followed by another experiment, which is, to my opinion, very important because it gave an interpretation based on the idea of coherence grating. Okay, and it is a very nice picture that combines optics and coherence in atomic physics. So here it uses the degenerate four-wave mixing. Okay, the mixing is something similar. It's blocked on this, but I want to insist on this view as diffraction. Okay, the idea is based on the interference of the input beam. The interference of one is Gaussian beam, the other is a vortex, and the interference produces a pattern like that, which is a fork pattern. And this fork pattern is imprinted on the atom and creates a fourth coherent pattern. And due to this fork coherent pattern, so if you illuminate the atom, so this picture with the reading beam, it will diffract on such a pattern, and due to this spatial point with this fork, it gives a vortex. Okay, so with this approach, the group have also demonstrate the four-wave mixing with a topological charge of 2. Okay, so now I have to explain some progress in phase shaping. Okay, which have allowed the development of the next experiment and development of the topics. As I have mentioned previously, the vortex was created by an amplitude mask. Okay, that means that you lose about 15% of the light. It is not a lot versatile, and you have an effect of the discontinuity in the pattern. Okay, diffraction of that, but it's working. After about the 2000s, there were many progress in phase mask, because the idea is to use the phase modulation of the beam to create a vortex, and there were many development in the domain, and also method to characterize the vortex and to measure the OIM. So I give here a small panel. So of the method are you have many solutions to create a vortex. For example, vortex plate, but also reflector, or something like that. It is applied in for electron, for radio frequency, And one of the system which is used a lot is a liquid crystal with a spatial modulator, and it is a device driven by a computer, so quite easy to use, which reproduce the phase hologram on the liquid crystal. It is here on the, you see my pointer? Yes, okay. No? Yeah. And you can, by this way, create vortices. You see here, we have created a vortex with a charge of 10, and here a vortex with a charge of 100. Okay. So another very important point is the method to detect the OIM. It exists a lot of methods. I have no time to give you an exhaustive list. And I have, in fact, only time to present one. You can use many interferometers, but I prefer to present you the one of the method, which is the tidal lens method. Okay, so the tidal lens method, it is a method where the vortex goes through a lens, a tidal lens, and when you tilt the lens, the ring becomes an ellipse. And then if you continue, if you change a little bit the angle, you will have an interference between the right and the left part of the vortex. And this interference produces fringes, and the number of fringes, the number of dark fringes, is exactly equal to the orbital angular momentum. So it is a sort of a self-interference method. And this method is easy to implement and easy to use to put in a setup. So we often use this method. Okay. So I have finished for the SLN, but I can show you here some example. We have some realization we have done. In my group, it has been realized by graduate students who have spent time in my group, and they have used SLN to produce here co-propagating vortices, but here no co-propagating, and here some random vortices. Okay. So now I come back to four-wave mixing with OIM for new things, for OIM transfer, storage, and retrieval. It was the center of the French-Brazilian collaboration we have with José and with Daniel. It gave some very nice paper. And I will focus on the storage, okay? So the idea for the storage is to use the delay for wave mixing and to use a lambda system. So in a lambda system, when you illuminated the atom with a lambda system with two lasers like that, you create a dark state, and the dark state, the expression is given here, is combined two ground state G1 and G2, and is uncoupled to the excited state. So it is protected and it can be used as a memory. And in the memory of this state, you have put the Rabi frequency, omega prime, of the two lasers. Okay. But you can also put the phase of the laser. So you can put in this dark state the phase through the value of omega, which is phase dependent. And so by this way, you can store in the dark state the OIM if you put on one beam. So it was done like that. So the first step of the experiment is to apply two beams. One is a vortex, then with a delay. We store the vortex, and after a delay, you can read this memory. You then suddenly change the dark state to a bright one, and you create a vortex beam. You generate a vortex beam. You can see here on this picture. So the signature of the result. So B is the input phase, L equal 1 dark fringes, and L equal 4. And in the output, you have the idler beam. So it illustrates the transfer of the retrieval of the OIM, and we have succeeded up to 4. So you can also put two vortex beam as the input. So then you can add the OIM or do the subtraction, okay? And here you have the table of mathematics of the OIMs, okay? So we have done other many interesting things with this subject. I have perhaps no time to delay. I prefer to show you some happy moments of the collaboration. So here has this dinner atom with Daniel and Jose and myself, and also a visit of an old abbey when Jose came in Orsay. I don't quite remember. He came sometimes via the coffee cup. He came also as invited professor by the university, and perhaps last pictures. It was a so windy day in Etretat, and so windy that it was difficult to stay vertical. Okay, you remember? Okay, it was very funny. So now I will continue and finish with my current and personal activity, recent activity. Yeah. So it concerns, it concerns non-degenerated, I don't know. I hear a sound.
Okay,
no, it's okay.
Okay, can go on.
It's non-degenerated for wave mixing in rubidium, which use this transition from the red to infrared and blue, okay? It is a transition where the atom is excited using Raman transition with two red lasers, and by decay, it produces an infrared at 5 micron and a blue photon at 420, okay? So this process is quite efficient if you are in this Raman transition, and this is a four-wave mixing process. The scheme is similar to that of calcium atom, which was used by Aspe and his collaborators in the past. Okay. And the question is the creation of this pair here, and in the presence of orbital angular momentum and the role of the optical turbulence in the process. So obviously we can predict that due to phase matching, we will have the conservation of orbital angular momentum. Here you have the setup. So it is a cell which is illuminated by the two lasers, the two red, and at the output, we observe all the parameters. We observe the spectrum of the blue light. We observe its intensity. We observe its phase through the tidal lens. And we also observe its propagation by traveling of the CCD, okay? And what we observe, there we observe that when we compare the input and the output, we observe that the blue carries all the orbital angular momentum. In this experiment, we put one angular momentum on this second red laser and 0 for the first one, okay? So this has been explained. It is confirmed by the mode analysis we have done over a large range, and the OIM conversion to the blue, so mainly to the blue, is due to mode overlapping and due also to the fact that this ratio of wavelengths is quite large, okay? So it explains the overlapping. So the process is quite efficient. We have realized of a wide range, as you show here, with many order of magnitude in our setup. And we explain the cutoff. The cutoff occur when the overlap is not good, when the vortex, the ring of the vortex, is out of the Gaussian. So if we change the size, we can enhance the cutoff. We can succeed. We have succeeded the experiment on up to 50. So we have also converted a OIM superposition. So the composition you see before. And we have recently done the conversion of two input vortices and seen the role of the relative handleness. You see here in the experiment, we put L1 and L2, and we look at the output, and if the vertex have the same handleness, we observe the sum 4 + 3 and 7. Okay, but with the opposite handleness, 4 and -3, we observe something completely different, and we in fact observe many modes. To explain that, we have to come back to the phase matching. What's new with these vortices? Curvature, it's okay to be more unfixed. The azimuthal phase, we have already discussed. But you have also the GUI phase. And the GUI phase depends on absolute value of L and on the radial number P. Okay. So if you consider this phase matching, and if you include the Boyd criterion states that Rayleigh range have to be equal to have an efficient nonlinear process, then you obtain a second condition for phase matching, which rely this absolute value and the radial P number. And if you look at this condition, you see that this condition on one depend on OIM and the other depend on the absolute value. It is the reason why the result is not the same for same handleness and opposite handleness. So If it's the same on the NES, you have a necessary radial number equals 0. The solution is the light, is a cyan line here. And if for opposite on the NES, it's allowed as p non-zero value. So you have many allowed possibility. In this graph, I have represented OML on X and P on Z. And if you compute the probability of the mode, so the weight of the mode, so you will obtain something like that for the same handleness, the mode with the maximum L equal L1 plus L2, and here many modes that explain this picture, okay, we have obtained. That means also that we have a strong entanglement of ORM in the output. So now come to the conclusion. So the conclusion has showed that such a study is open to other subjects. You know, now you have a study of quantum fluid. Okay, in quantum fluid, just to have a word, is based on the analogy which exists between the Helmholtz equation in a nonlinear medium. And if you use this transformation of the field to rho and v, and v, you can connect this equation to the standard fluid equation. So that means that you can use light to observe a shock wave, to observe turbulence, to observe a soliton. So in my problem, I could study the mixture of quantum fluid. It is also connected to quantum simulation and quantum computing. So just to give an idea, if you consider the same problem, you can compare this equation, Helmholtz equation, with the Kerr effect to the nonlinear, to this Schrödinger equation problem. It's quite similar if you change the time on Z, if you have no potential, and if you define the correct constant here to have the correspondence, okay? That means that you can, with my system, use it to look at system with many colors, so it's equivalent to many species in this problem. So, of course, in this context, we have to understand a little bit more how the HM is shared in the four-wave mixing, and here in the spontaneous down conversion, because it is the center of the problem, and we have to understand the ORM in detail, the ORM entanglement, and how to change the ORM entanglement. So I thank you a lot. I finished just to show you a picture of the co-authors of this work, and I want to insist about the work of Aurélien Chopineau. It was a large part of its PhD work, okay? And I have also to mention the institution, so CNRS University, and also the agency for the money. Okay, so thank you very much. Yeah, finished.
Okay, Laurence, thank you very much for this very didactic and clear talk. Really appreciate it. So we do have time for 1 or 2 questions. So please. Any question? So I just have a comment. I don't know if you remember, but you were here by the time we thought we had discovered a new method to measure the topological charge. Then we got very excited, but soon we discovered that this was already published. So
yeah,
that was
I was in the experimental room with the student.
Yes,
remember?
Yes. Rafael.
We do not understand. It was misaligned. We do not understand.
Anyway.
And finally, we found this paper of Beatty I have mentioned. Okay.
Yeah.
But now a lot of groups use this.
Use it. Yeah. Okay. Any other comment or question? Okay. If not, thank you, Laurence.
Thank you.
We will continue. Sure. Okay, so we should move to the next talk, which will be presented by Ruben Kaiser, and I would like to invite Anderson Gomes to introduce him. Your microphone is up.
I needed permission to that. Now I have permission.
Oh, I
so,
already.
Yeah, it's okay now. So it's a great pleasure to introduce Ruben Kaiser, and also thank Tabosa and congratulate all the organization. And Ruben, as you know, the best is always the last one. So I'd like to say a few words about Ruben, whom I met several years ago, perhaps around 10 years ago. So Ruben is a APS fellow. In 2011, he also won the Prix Ernest Deschelles from the French Academy of Science in 2013. And the Grand Prix 2020, not the Grand Prix for Formula One, but was the Grand Prix de l'Institut Grand Ducal de Luxembourg. So more recently, he was awarded an advanced ERC grant, which showed all the international and the national recognition of his work. So if we go back a few years, he's known in the field for many contributions since the beginning of his scientific career, still at the Institut d'Optique, where he was a pioneer in novel subrecoil cooling schemes, which he introduced. Also working on atom optics already on that time, and he was some important work on mirrors for atoms. And then in 1996, he moved and started his own group in Nice, exploiting mesoscopic physics with cold atoms. His results on big subradiance, for instance, have attracted a lot of attention and had also potential impact for high precision atomic clocks. And more recently, and certainly he's going to mention in his talk, he's devoted all his knowledge to interaction of large clouds of atoms and start a number of very important investigations, ranging from coherent backscattering of light by cold atoms, Levy flights of photons, a very important subject, random lasing in cold atom. This is fantastic, and that leads to what nowadays is known as astrophotonics, but he's going to be certainly the first one to observe random lasing in space. So certainly he's going to talk about this, and I'm very pleased to have been in Nice for 1 month. We had some nice work there. Some papers being written right now. Ruben, just wait. Yes, please. The waves, the electromagnetic waves are all yours to talk.
Okay, thank you very much. Let me see if I can share the screen. Can you see my my screen?
Yes.
Yes.
Yes, but it's not in the presentation.
Yeah. This will just a a second. Is it now better? Can you see it now, full screen?
No, not yet.
Yes, okay.
It's okay? No, okay, now it's okay.
Okay, some delay. That's okay.
Yes.
Okay, very well. Okay, so first, thank you very much, Anderson. I'm happy to to see you again, and thank you for the kind words. And I'm waiting for the paper, right? And thank you, the organizers, for this fantastic meeting. It's really a pity that we cannot meet on site, because I think all of us, we have so many friends, so many good memories of all these connections, and I will only give a small glimpse of everything I experienced during my time in Brazil. So I would need 2 days to speak about everything. So half an hour is really not fair only to give me half an hour to speak about everything I did together with my Brazilian friends. So let me, because it's getting late, so just a quick start. I will skip science a little bit. Let me just speak about how I consider, I value your invitation. So I read many years ago a book about cultural shock or exchange, and there was someone who went to Japan, and he was treated very well, and so he had a nice room. One day he came to his hotel room and it was changed. He didn't get any notification of this, and so he was a little bit upset. And then when he asked for explanation, they said, "Okay, this we only do with our best friends. Only the best friends we can adapt very quickly without telling them, because they belong to the family." So in being the last speaker here, I consider this to be a mark of being best friends with my Brazilian colleagues. Thank you, Tabo. Okay, so let's now come back to my talk. So I will, initially I wanted to speak about collective photon atom interaction, but then I adapted in the last days a little bit to be more specific to our Recife connection. So first here you see a picture, let me see, you should be able to see my laser pointer. A picture on the left is the NIS part, and on the right is Recife. And both of us, we have a nice island next to our cities. So in our case here, we have Porcorol, where I every now and then organize conference. And you, of course, you have the best one, the best ever, Fernando de Noronha. I will come back to this later. So this is really a very nice place, and everyone who has not been there yet should try to get there. Okay, so here is now a list of the team in NIS, which I have to mention. One thing I find really important in all this collaboration is not only that we can meet our friends, but it's also important to pass over this tradition to the next generation. And I'm quite happy that Mathilde, for instance, she's already very eager to collaborate a lot with Brazil, so that's very good. William and Guillaume, they're a little bit less traveling persons, so it's a bit more difficult for them to get them over to Brazil. But Mathilde has been there, and she will come back very often, so I'm very happy with this. And in bold here are all the people from Brazil with whom I have interacted in the past, and in yellow the ones from Recife. So you see the bold part is a very important part of all my active collaboration. So Brazil for me is really the strongest collaborating country, and it has been so for many years. And the focus of with whom I work shifts every couple of years, but I have constantly been in touch with Brazil. And this is, you will see some of the work. I will try to highlight some of the work with some of these people, but I cannot speak about everything. Okay, so what we do typically here in Nice, as Anderson told, is that when I move to Nice, so I also try to give lessons to people who start new groups. It's very important not to get blown by the old competitors who try to take all the low-hanging fruit. So it's very difficult to find a niche. So our niche here was only one very specific thing, which was to build a very large magneto-optical trap here. And this has been known before. You need large laser beams to get this. You need a little bit more power to do it. But once you have this, you can do a lot of physics that people cannot do. So our main technical advantage actually was just to have a large glass cell to be able to take large laser beams and to get more atoms. All the rest was just a consequence out of this initial geometry selection. So from this, we studied a lot of collective effects, going back scattering, Dicke subgradients. We now want to go to Anders localization. I will not speak about this, even though this is my main life project, basically, typically. but we have done a lot of pattern formation. This mainly is the work of Guillaume Laverie. I will not speak about this neither. We have done a lot of instabilities, but I will speak a lot about random lacing. And random lacing from cold atoms, how we start from cold atoms, and stepwise come closer to look for random lacing in space. And if time permits, I will speak a little bit about levy flights, because this has been in constant interactions with people from Brazil and from Recife and Europe as well. Okay, so the outline of the talk is, in the first 2 hours, I will speak about random lacing, and for those who are not sleeping yet, I will speak for 2 hours on levy flights. No, I'm kidding. 10 minutes and 5 minutes maybe. Okay, so how does this start? So, the goal is to make a connection between cold atoms, and basically, if you have a large cloud of cold atoms, you can have photons doing a lot of random work in this sample before escaping, and you want to add gain to this, and there are different ways to do it, and you want to simulate astrophysical objects. So in some sense, this is a simulator. I don't know if it's a quantum simulator. It's, you replace one system, which would be astrophysics system, by another system to understand the dynamics and the signatures, how to observe it. So it's kind of a simulator. So the goal in the lab is to find good spectroscopic signatures of random lacing which could occur in space. And once you are convinced that you have the right tools, then you go to the telescope and look for the right signature. Okay, so the first thing is you have to start with gain. And so this is known, I've seen now that the French-Brazil connection was a lot about four-wave mixing. So this is, I didn't know all this four-wave mixing connection. Now I understand why Barbosa imported this four-wave mixing to NIST. I didn't know that, but okay, he basically imported this technique to us. So there are different gain mechanisms. If you take a resonance system, so there's mono gain about the tool with the rest level atoms, you can explain this. There's recoil-induced resonance or Rayleigh gain. There's Raman transitions, and there's four-wave mixing. So there's different ways, and they are all basically more or less known to induce gain in atomic vapor. So we did this with cold atomic vapor, and here are some experiments which have been performed, well, basically by Tabosa, I would say, and by some other collectionists. But when Tabosa came here to this, he showed us how to do efficient forward mixing. And so we did this. What we had is this large cloud of cold atoms. So the signals were bigger, basically because we have more atoms. But Tabosa really showed us how to do this forward mixing. And so we get very efficient reflection. And at some point, even in double path, we get a huge gain in this. So we could get self-oscillations. So that was a tremendous amplification of modes which initially are empty, using these atoms in the four-wave mixing condition. So all this is an expertise which we did not have, but Tabosa showed us how to do it. And then, so once it's known how to put gain in the atom. Then we need to make a little bit more. So we want to see if we can go above the threshold. So what we did then is try to use some of this gain mechanism and put mirrors around the cold atom cavity and see if you can make it lace. And this works. Actually, it's not so difficult. And what we found, we took mirrors outside of our vacuum chamber with uncoated windows. So it's really a lousy cavity. So it's what is now called the bad cavity limit, which is very interesting for many aspects again. But so in this bad cavity limit, we found a multitude of lacing regimes, and I will not go into the details, but all of these lacing regimes, except one, is basically well understood in terms of polarization, of threshold, and so on. So it's quite easy to do this lacing. Something we did not do at this time, to continue, we didn't look at the spectrum of the light coming out. We did some very quick measurements, and what we saw is that some of these lasers have an extremely narrow line, emission line. But for some reason, we didn't pursue this. And so, okay, sometimes you miss things. Nowadays, this is very well known. It's a big issue about super radiant lasers, which is followed by Thomson and Gilla now. We basically missed it. I think we could have done this in those times, but basically we missed it. So this happens, you miss things. It's don't be too depressed if you miss things. This is normal that you miss things. I think here we missed a great opportunity, but we didn't understand everything which was at play. Okay, so then you need to go for random lacing. So gain, we showed that gain is possible. Now we want to combine gain and multiple scattering. And So in a typical laser here, you have the mirrors which fold the path of the photons many times across the amplifying medium, and this is how you overcome losses. In a typically random laser in 3D, you have this multiple packed scattering path, which is kind of a spaghetti which is folded, and the length of this spaghetti has to be larger to overcome the losses. So the losses are basically when the photons leave the surface, so it's a surface effect, and the gain is in the volume. So it's known that there's a critical volume where the volume will be larger than the surface, loosely speaking, and you will overcome a threshold. It's like an atomic bomb. It's also called the photonic bomb. And so the problem is that if you use atoms as scattering and as gain medium, can you have gain and scattering with the same atom? Because you could think that you bleach the atoms, you saturate the atoms, and then the scattering goes down. So the question was, can you combine and gain and scattering in the same atom? So this was a little bit complicated, but a lot of work together with people from the random scattering community, Remy Carminati, we were able to show that if you take the atomic polarizability alpha, there is a threshold. So it's possible, if you know the atomic polarizability, to combine and gain and scattering, and there will be a critical size, which we now call a critical optical depth, to reach the random lasing threshold. So it's possible. A threshold exists, which was not obvious before. And the numbers are okay. It's not easy, but they are okay. The main question is how to observe it. What would be the best signature? And for this, just a short sidewalk. In a regular laser, it's quite easy to know when the laser is running. You look at light going through the mirror, and if there's no light, it's below threshold, and if there's more light, it's above threshold. But basically what is happening is that the laser redirects photons, which would be scattered in other directions, into one spatial mode. So you don't really generate a lot of more light. You just redirect the light in the same mode. And in the 3D random lasing, you cannot benefit from this spatial enhancement. So the enhancement is just a faster circulation in the gain medium. So it's much weaker than you would see in a regular laser with the directed output beam. So the question is how to detect the random lasing first. So there are a couple of techniques which are possible. Looking at the fluorescence is one, trying to look at the spectrum, intensity correlations, absorption imaging. So okay, so we started with one specific gain mechanism, which is hyperfine gain, because it's easy to make a large population inversion between different hyperfine levels by pump and repump lasers. And we added additional gain scattering by tuning the gain transition to a forbidden transition for the pump. So the pump would not see this transition, so the gain is not affected by the scattering is affected by this transition. So this was kind of a trick using atomic physics to reduce the critical optical depth by almost 1 order of magnitude. And then when you look at the total fluorescence, if you increase the number of atoms, the optical depth by compressing the cloud with a constant number of atoms, that's important. What you can see is that at some point you have the gain curve, and at some point where the scattering is enhanced, you get this additional peak in fluorescence. So this enhanced circulation, which is a signature of combination of gain and free scattering. So we did a lot of complex modeling to compare our experiments to models which are shown here below, and basically we could show that this model is consistent with our experimental observation, and it's the signature of random lasing in the vapor of cold atom here with gain and multiple scattering. Okay, so this is fine, but this is not everything. The question is, this is not the easy way to look for astrophysical lasers, because in astrophysics, you cannot tune a frequency. The star is the star, so you cannot really choose a pump frequency. So we need to find other signatures for random lasing in space. And one possible possibility is, as in regular lasers, is to look at intensity correlation. We know that if you just look at the spectrum of some light emitters, you cannot distinguish a spectrally filtered incoherent source with some pinhole from a laser. You need to go to intensity correlation. And so this is what we developed first in hot vapors to get access to fast bandwidth. And then we also tried to do this. We did this together with Anderson on another random laser, a random fiber laser. And what we could show in this setup, which is what we discussed with Anderson in the paper, it has to be written, we showed that there's a threshold and that intensity correlation, indeed, below threshold, there's photon bunching, as you expect from incoherent light. And above the threshold, this photon bunching at short delay time vanishes. We found other things, strange observations, but this is the main signature which we can use as an identification as a threshold of random lasing for in astrophysics. Okay, so now, so basically we are more or less ready as a signature. So it will be intensity correlation for astrophysics. Now we have to go to the telescope. So what we also developed is instruments to install on telescope. And so this technique is well known. Andre Brown and Twist did this in the 60s on 30 stars, they measured this. But basically this technique was completely stopped and forgotten after the mid-70s. And so we reintroduced this technique with modern quantum optics, with photon counting modules and part electronics, fast correlators, everything basically which is now used in quantum communication. So we use the same technique which comes from our cold atom community and apply to the astrophysical community, which who are not used to this technique. So we showed that you can do in the photon counting regime intensity correlation. You can measure the angular aperture of the star as Andre Twist with the modern technology. So we measured, for instance, one star, and now we push this. We can propose this as a calibration for the distances of the universe. So there will be new applications coming out of this revival of intensity correlation in astrophysics. And together with our Brazilian friends, which are here, we have had access to a large telescope, a 4-meter telescope in Chile in 2019. And this allowed us to show that our module, which is a box like this, we can transport it over the ocean. We go there, we install it. We had only one afternoon to install it. And in the night, even though it was a bad night with a lot of clouds, a lot of wind, full moon, everything astrophysicists people hate, we could see bunching on Ithaca, which is my favorite star for random lasing. So this showed that our module is robust and transportable. And except that the pandemic now stopped us, we have been planned to install, and some of our materials already installed at the VLT in Chile. And so so it has been reported next February. So we should go there next February to try our intensity correlation measurement on the big telescope. So this is a growing community. Many other groups now, since we saw the first technique, other groups have seen similar things. And so this is now the race is open to look for quantum optics in space. Okay, I don't know. Let me see. So time is running quickly. I will quickly go from the other topic, which is not exactly related to this, but it's also a very strong Brazilian connection, which is how to go from diffusion to level slides. Tell me how many people are still there, or how many people are not sleeping? Let me see if I can. I will make a very quick tour. So in normal diffusion, you have a diffusion coefficient, which is shows you how an excitation spreads. And this diffusion coefficient is well defined if the mean free path and the second moment of the step size distribution is well defined, is finite. And this is the case if you have an exponential law, how far you propagate before you change direction. So in most of the regular scattering, if you take milk, light in a glass of milk or white paper, there's an exponential distribution, and then the mean free path and the second moment of the distance, propagation distance is well behaved, so you get a normal diffusion. But if you don't have an exponential law for the step size distribution, but if you have a power law, and if this power law has an exponent which is very small, then the second moment might not exist, or the first moment might not exist. And so this happens for this coefficient nu below 3, then the second moment diverges. So this is the case where there's no longer a diffusion coefficient. You can no longer define the diffusion coefficient, which would be infinite. And if it's below 2, then even the mean free path diverges. So the question is, can we do this type of studies in atomic physics? There's been some reason why we came to this, but I won't have time to explain the historic where we led to this. But basically, we came first up with the system. So the main ingredient is to measure this step size distribution. How far a photon goes before it changes direction, to measure this law. So you need to track a photon. So if you have a radioactive photon, you would label and measure the distances. That would be great. But it's very difficult to find radioactive photons. So we had to cheat to find a trick how to measure this step size distribution some arrangement. So we found a trick with the multi-cell arrangement. I will not go into details, but what we could show is that if you take a laser beam in going to this atomic vapor cell, you find an exponential decrease, which is this curved figure here in the log-log scale. But if you go in the multiple scattering limit, then it's becoming a power law, and the exponent is below 3, which shows you that there's no diffusion coefficient which can be defined. So again, the Levi-Flight regime for photons in this hot atomic vapor. And so this has been work where we had a collaboration with Martine Chevrolet, who and with Marcos, they were having visiting here us in Nice, and following this visit, she was doing a lot of simulations to understand to get the right. You see the agreement between the model and the experiment is excellent here. So this was the contribution of Martine and her group in João Pessoa. Later on, we found different ways how to measure this Levy coefficient in easier way, and following this easy technique, we had a collaboration with a colleague of Martine, Thierry, in João Pessoa, and we could show that if you take a buffer gas, you can even get to a regime where this exponent is in a regime where even the mean free-path diverges. So you get really very strange propagation of photons in this atomic vapors, and so this is ongoing research. It's important for statistical physics, and it could be important also in applications if you have hot vapors for quantum technologies. It's important to know how this light scattering behaves. Okay, with this, I will come close to my end. I cannot discuss everything I did with Brazilian friends. I have collaboration, ongoing collaborations with people in San Carlos. Romain Bachelard is basically one of my main collaborators right now. Also, he's coming again back for a sabbatical year. But so I have many collaborations, and all these people I meet regularly, and I will be very happy once we can travel again to meet. And I will just finish with some pictures. So this is a picture when Tabosa visited us 2003 or 4, I forgot exactly when. I was really impressed, I have to say it again. When we have visitors, typically visitors stay behind experiment like this and they don't touch anything. And they wait for the students to touch the knob. Tabosa, in a few days, he was pushing away everyone. He was doing the experiment and very well. So I was really impressed how quickly he took over a new setup which he didn't know before. It's really impressive. I also visited with my family Recife, and so this is a picture. Again, thanks to Tabosa, we were able to put our kids in the kindergarten in Recife. They enjoyed a lot. They didn't speak Brazilian, Portuguese, but they get a lot of friends. It was so welcoming. It was really amazing. Here's a picture of our family. I don't know where this is, but we actually puzzled with my mind where this is. So please at some point, someone tell me where this is. And so no one can stop this connection without a picture of Rios and his famous boat. So I got a trip on the boat, but only one day, not up to Fernando de Noronha. But I have been in Fernando de Noronha for a conference, and this was helped by Anderson, who got this right connection to do this. And this is a group picture you do when you're in Fernando de Noronha. So with this, I will stop here, and I thank you for your attention. And again, thank you so much, all the Recife team, all the Brazilian colleagues. It's really fantastic, and I think it's really, really important to transmit this connection and collaboration to the next generation. This has to go on for many, many years and many generations. Thank you very much.
Thank you, Romain. Really fascinating talk. Thank you very much. So the question, the section is open for questions, comments. Please. I'm sure that you do have questions.
So I have a question for everyone. If you have pictures of our collaboration between France and Recife or Brazil, send me some pictures. I didn't find a lot of pictures quickly. I know that Anderson had a picture somewhere, but I didn't find it. So if you have a picture, or I will be happy to collect the pictures.
Deus.
I have a lot of pictures from you.
I have one question. It's for Robin and could be for the other colleagues who collaborate in this work of the random lasers. The thing is, let me see if I put my question in the context from the conventional laser as you explained. When you look for a gas laser, the atoms or molecules of that laser, they are randomly distributed. And yet the mirrors select one single direction of laser. Could you comment on how strong is the difference between this and leaving the active units random distributed and then making what's called the random laser?
I think, okay, so obviously, I don't know, Jörg is in the audience, I don't know, maybe other people are expert on lasers, which I'm really, but I think basically in lasers, what you want to have is a lot of gain and no scattering in one direction. And so this is the killer for good lasers. So if you develop semiconductor lasers, you don't want to have a lot of scattering out of the main mode. You want to have gain in one direction. That's my understanding. In random lasing, actually, if the photon is changing direction, it's not a problem. The photon is not destroyed. It's just changing direction. So that's not the problem. But it's difficult to know how you amplify it, because all the light going in is going out at some point for atomic. But you have to know if it has been changing its frequency and its coherence, time coherence. So the spatial aspect is much clearer in a regular laser. Even if the atoms are random, the photons will be, you have one photon, the other one will be amplified and go in the same direction. They amplify. They all go in the same direction. But now if you have amplification and then all of the four photons change directions together, for a regular laser, this is a loss. But for a random laser, that's not a loss. But I don't, probably it's not a good answer for your question, but it's just that scattering is not a loss mechanism for random lasing. The loss is at the output of the surface of the system, not inside. And I think for regular laser, scattering is always a loss. But, okay.
Okay, any other question? So let me just ask a question a bit. How I mean, I see that it's very hard, I mean, very difficult to say what's the power that your random laser emits. You cannot measure it.
No, okay. So I think we could estimate it. If you want to measure it, you would need to, okay, in 1D, it's easy. So in 1D, it's easy. In 3D, you would need to have an integrating sphere and to make a spectral selection. So you could put a filter in an integrating sphere and then measure the spectrum of the power. It's not very easy to do it with cold atoms, but if you assume that there is a spatial isotropy and if you know the solid angle, you can estimate it. In a 1D system, it's easy to do. Understood?
Anderson.
Yes, yes. A little bit on the Rio's question. Rio's very naively, you can imagine that you have your conventional laser with the atoms, they're all going around, as you say, but then you put two static mirrors. Now you are very clever, like Letakov was, and then say, okay, now I want these mirrors here and here and here and here and here, moving around all the time. So that's what the scatters do. And then comes to Tabosa's question. Because of that, now I say, okay, what we have is a multi-directional laser. There are lasing all over. If we put that, this is something that can be done. I don't think anybody did, but it's, in principle, it's easier to have not for particularly for Robin's cold atom laser, but for one of the dye lasers where everything goes around. If we put this into a integrating sphere, we should have a number that's quite close to the laser output integrated in all directions. So I think it can be done from this point of view, but in the case of robots, it can be estimated, as you said. And in one dimensional is, of course, much easier. But I think it's along those lines. So Tabosa, we buy an integrated sphere, let's measure this.
Okay. Okay, I got it. Any other question?
We bought already, right?
City?
We bought the integrated sphere already.
Yes, we bought it. It's arriving.
Oh.
Okay. Okay.
This progetto di Tamar from Fernando Ronde.
Good. Good. Okay, so I think we are getting to the end. So I just want to say a few words about our symposium. I think it fulfilled its main goal, which was to retrace this long trajectory of collaboration in physics between our two countries. And at the same time, I think it to bring and show to the much younger students how important is collaboration, cooperation in science. I think, as you know, collaboration can lead to synergy. And I think we have seen, I mean, what we saw in this today was clearly, and it was clearly pointed out by Martial Ducroix. I think the France-Recife collaboration in physics was and continues to be important and profitable for both sides. So with these words, I really would like to thank you all, and also thanks all the speakers, the authorities, academic authorities, and all your you all, I say. But before I close the section, I just want to know if someone else would like to make any comments or any comments, let's say.
Congratulations to you, and thank you, Tabosa, and to all speakers. I think the whole meeting was very interesting. And as you said, we hope that the young people realize how important it is for science and international collaboration. Thank you all. Thank you, Tabosa.
Thank you.
Tabosa, if everybody appears on the screen, and then we can make a picture of most of us here on the screen.
As you saw it this morning, I'm not an specialist
I know, Tabosa, I know, but we can do that.
Please, maybe I should ask Bruna. Maybe she can set up the screen for this.
See, open your camera.
Closing photo.
Yes.
I think she can put up to 36 people in the same screen.
Yeah.
Can you, Bruna?
Yeah. Let me put everybody on screen.
But you can carry on speaking. No problem. It won't appear.
Yeah, one comment. I think it's very important to get students involved very, very quickly at their PhD level or quickly afterwards. My first contact to Brazil was when Vanderlei came to the lab where I was doing my PhD. So it's very important to get them very quickly, not wait until they are well recognized or established researchers. You have to make the contact for them when they are very young.
Everybody ready for the picture?
Okay.
I'm ready.
Everybody is ready.
Josh, you are on the beach.
Yes.
Good.
That was my purpose, to be in Recife today, but it's not possible.
It looks like a Recife beach.
Yeah, and it's very windy.
Yeah, it seems to. Okay, let's move for the picture.
Yeah.
I took some screenshots and I send you to you, Professor.
Very good.
Okay, thank you. Thank you very much.
Yep.
Okay.
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 Hey,
Thank you all. Thank you all.
Have a good afternoon for you and good night for everybody.
In 10 years from now, we'll do another one. I hope everyone here could participate.
Okay, we will be ready if we are here.
And you have to invite us now. You invite us officially. So
yeah, that's already an invitation.
Yeah, good.
Okay, ciao everybody. Goodbye. Bye-bye.
Bye. Really.
Goodbye.
Bye.